Good day, everyone. I'm Tim S. Trinidad from the Department of Physiology, and I was tasked to give you this review on respiratory physiology. Okay, so what I intend to do for the next 3 hours is discuss to you these 13 concepts which deal with respiratory physiology. Let us now discuss the first topic, which is the changes of O2 tension from the atmosphere to the venous blood. So this is the first interactive question. Which of the following occurs to the atmospheric air during ascent to high altitude? A. Is it atmospheric pressure increases? B. The FiO2 remains constant. C. Nitrogen concentration remains constant. And D. The inspired oxygen tension increases. So what I want you to do is pause the video, try to answer it, and once you have an answer, resume your viewing. So let us now discuss the gas composition of atmospheric air, which is composed of nitrogen, oxygen, carbon dioxide, and other trace gases. Here are the relative concentration of these gases. 78% is nitrogen, 21% is oxygen. Carbon dioxide is way low at 0.03%. So if we're going to inhale a tidal volume of 500 cc, okay, 78% of the 500 cc or 390 is nitrogen, 21% of the 500 tidal volume or 105 is oxygen. So let's now discuss the inspired gas tension of atmospheric air. At sea level, the atmospheric pressure is 760 millimeters mercury. And therefore, if we want to compute for the inspired nitrogen gas tension, we just multiply 760 with the concentration of nitrogen, which is 78%. And therefore, we come out with the inspired nitrogen tension of around 593. So if we want to compute for the gas tension of oxygen in inspired air, okay, or the PiO2, it's 21% times 760, and therefore the inspired air gas tension is 160. Now, if we add everything up, we come out with a total of 760. This is based on Dalton's law, which states that the total pressure is the sum of the partial pressure of the individual gases. Now, let us discuss the changes in atmospheric pressure from sea level. Here is a graph showing to you the relationship in the x-axis of altitude and the barometric pressure on the y-axis. And as you can see, based on the relationship, okay, the greater the altitude, the lower is the barometric pressure. Now, here is another graph showing to you now the relationship between the depth beneath the water surface in the x-axis and barometric pressure in the y-axis. Again, you can see that based on this relationship, the greater the depth from sea level, the greater is the barometric pressure. So if we put these two graphs in an equation, okay, you can see that the greater the depth, the greater the atmospheric pressure. The greater the altitude, the lower is the atmospheric pressure. Now here's a table which will show you the different oxygen tension of inspired air at increasing altitude. As we discussed, with increasing altitude, for example at 7,000 feet, the barometric pressure decreases to 584. And when we try to compute for the oxygen tension, okay, we just multiply 584 times 21%. So the inspired oxygen tension goes down from 160 to 122. Now, what will happen if we further ascend to 36,000 feet? Will the PiO2 be higher or lower than the 122? Okay, at a higher altitude, the barometric pressure decreased further to 170, and 21% of that is 36 millimeters mercury. So what I'm driving at is with increasing altitude, the FiO2 remains constant, but the atmospheric pressure decreases, and consequently, the inspired oxygen tension decreases. So let us apply that principle with that of air travel. Now, during international flight, okay, the cruising altitude is around 36,000 feet. And at 36,000 feet, the barometric pressure is 170. The inspired oxygen tension is 36, and this is not compatible with life. So what will the airplane manufacturer do? They're going to pressurize the cabin pressure to 7,000 feet. And at 7,000 feet, the barometric pressure is 584, and consequently, the inspired oxygen tension is 122, and this is compatible with life. Thus, if we apply that principle of air travel in this table, we can see that the cruising altitude is 36,000 feet and the inspired oxygen tension is only 36, and that is not compatible with life. So what would the airplane manufacturer do is they're going to pressurize the cabin to 7,000 feet and the inspired oxygen tension will be 122, and that is compatible with life. Thus, during air travel, the cabin is pressurized to 7,000 feet as if the passengers are breathing 15% FiO2. Let's now move on to deep sea diving and Boyle's law. Boyle's law states that gas volume varies inversely with pressure. Pressure times volume is constant, and therefore if pressure is going to increase, the volume is going to decrease. This is illustrated by this cartoon over here, wherein a person is going to dive to 165 feet of salt water. Notice that the barometric pressure increases from 1 to 6 atmosphere, and notice the corresponding decrease in the gas or the lung volume from 100% down to around 10%. And therefore, the greater the depth, the greater is the barometric pressure, the lower the gas volume is. The sudden ascent increases gas volume, and this may predispose to barotrauma and air embolism. And this cartoon will illustrate that. If, for example, at 165 feet, this is the gas volume, and the diver is going to suddenly ascend, the pressure is going to decrease tremendously, and the volume or the gas volume is going to increase and may cause rupture of the alveoli. Thus, you have barotrauma. This air that's going to escape from the alveoli may go to the blood vessels and produce air embolism. Now, in Henry's law, it states that the amount of gas dissolved in a liquid is directly proportional to the partial pressure of that gas. And therefore, the greater the depth, the greater the pressure, the greater is the molecule in liquid form. This is illustrated by this cartoon over here, wherein at sea level, for example, 5 of the 15 nitrogen molecule is in liquid form. And when a person dives to around 50 meters, around 10 of the 15 nitrogen molecule is in the liquid form. This is another way of looking at Henry's law. If, for example, a person is going to dive around 450 meters, the barometric pressure will increase from 760 to 4560. Consequently, the nitrogen tension will increase from 593 to 3556. Now, nitrogen is a fat-soluble substance. It crosses the blood-brain barrier. It may act as a pulse neurotransmitter, and the diver may manifest with nitrogen narcosis. Aside from nitrogen narcosis, because of Henry's law, a deep-sea diver may develop decompression sickness, which is usually secondary to rapid ascent. Again, if we go back to this illustration here, if there will be rapid ascent, most of the molecule in liquid form will be converted to a gas form. It is similar to opening a bottle of Coke. If you open the bottle of Coke, there will be a tremendous decrease in pressure here, and there will be bubble formation. And this is what happens during decompression sickness. A rapid ascent will cause bubble formation in all of the tissues, including inside the blood vessels, producing air embolism. Thus, during deep sea diving, a diver may develop barotrauma and air embolism due to Boyle's law. He may likewise develop nitrogen narcosis, decompression sickness, air embolism due to Henry's law. So we go back to this question again. Which of the following occurs to the atmospheric air during ascent to high altitude? Atmospheric pressure increases. That's false. We know it decreases. FiO2 remains constant. That's true. Nitrogen concentration remains constant. That is likewise true. And PiO2 increases. That is false because PiO2 is equal to barometric pressure times the oxygen concentration. So the correct answer for question number 1 is FiO2 remains constant and nitrogen concentration remains constant. Moving on to question number 2, which of the following explains why the arterial oxygen tension is much lower than the alveolar oxygen tension? A. Upper airway humidification of air. B. Low atmospheric pressure. C. BQ relationship in the normal lung. And D. Left to right shunt due to bronchial circulation. Again, I like you to pause, try to answer, and then resume. Now, these are the different compartments where oxygen tension may differ. You have atmospheric air, then you have air in the airway, then you have the alveolar air, then you have oxygen in the end capillary, oxygen in the pulmonary vein, oxygen in the blood in the pulmonary artery, oxygen in the tissues, oxygen in venous blood, oxygen in the pulmonary artery, and finally oxygen in mixed venous blood. The inspired oxygen tension is 160, while that of the oxygen tension in the airway is 150. The question now is, why is there a decrease in the O2 tension? Illustrated here are the functions of the upper and the conducting airway. The ambient air or the atmospheric air has a temperature of 22 degrees centigrade and a water vapor pressure somewhere between 0 to 10 millimeters Worker. As it passes through the upper airway, you can see that it is warm and humidified. As it goes further into the conducting zone, it is further warm and humidified. So the cause of the decrease of the O2 tension from 160 to 150 is due to the humidification of air by the upper airway and the lower airway's conducting zone. So from 150, the oxygen tension in the airways goes down to 104 in the alveolar air. The reason for this is the diffusion of oxygen along the AC membrane. As mentioned, alveolar gas diffuses along the AC membrane into the blood in the pulmonary capillary. Initially, the mixed venous blood is 40, and at equilibrium, the end capillary oxygen tension will now be 104 plus minus 2. If the BQ relationship of the respiratory unit is 1, then the end capillary O2 tension will be 104. However, if the BQ relationship of the respiratory unit is less than 1, then the O2 tension will be less than 104. On the other hand, if the BQ relationship is more than 1, then the end capillary O2 tension will be more than 104. On an average, the BQ relationship of an upright lung is 0.8. And therefore, if we average all of the respiratory units and capillary O2 tension, it is going to be less than 104. From an end capillary O2 tension of 104 plus minus 2, the arterial oxygen tension now becomes 100. Now, what is the cause of the decrease from 104 to 100? Primarily, it's due to the presence of shunts. And the two types of shunts could either be alveolar shunts. These are the respiratory units with a low BQ relationship, or the anatomic shunts. This is an example of your two anatomic shunts. Okay, you have the bronchial vein to the pulmonary vein anatomic shunt. Okay, the bronchial vein contains deoxygenated blood coming from the bronchial circulation. It is admixed with the oxygenated blood of the pulmonary vein. The Tibian vein left ventricle anatomic shunt, as shown here, the deoxygenated blood coming from the left ventricle drains directly into the left ventricle, which contains blood rich in oxygen. From the arterial blood of oxygen tension of 100, the tissue O2 tension goes down to 23. This is primarily because oxygen is consumed by the mitochondria for oxidative phosphorylation. From a 100 arterial oxygen tension, the oxygen tension goes down to 40 in the venous blood. This is primarily because of the oxygen extraction by the tissues. So we go back to this second interactive question. Which of the following explains why the PaO2 or the arterial oxygen tension is much lower than the alveolar oxygen tension? So it's asking us why is there a difference between the alveolar oxygen tension and the arterial oxygen tension? Is it due to upper airway humidification of air? It is false, because that will explain why the inspired oxygen tension is different from that of the alveolar oxygen tension. Is it due to the low atmospheric pressure? Okay, that will not explain the difference between alveolar and arterial. The low PiO2 will explain the difference between the inspired oxygen tension and the oxygen tension in the airway. Is it the BQ relationship of a normal lung? Yes. Okay, that is responsible why there's a difference between the alveolar oxygen tension and the end capillary O2 tension. Okay, as I mentioned earlier, the BQ relationship of all of the respiratory units on an average is 0.8, and therefore the end capillary O2 tension is expectedly to become less than 104. Now, is the left to right shunt due to bronchial circulation responsible for the difference between the alveolar and the arterial blood? Okay, false, because it is the right to left shunt which is responsible why there's also a difference between the alveolar and the arterial oxygen tension. So the correct answer for question number 2 is the BQ relationship of the normal lung. Now let us move on to the second item, which is lung volumes and capacities. The third interactive question is that which of the following is equal to functional residual capacity? A. Inspiratory reserve volume plus tidal volume. B. Expiratory reserve volume plus residual volume. C. Total lung capacity minus vital capacity. And D. Vital capacity minus inspiratory capacity. Again, I like you to pause, try to answer, and then resume. Tabulated in this slide are the four lung volumes. The mnemonic is ITER, I, T, E, and R. Number 1 is inspiratory reserve volume, or IRV. Number 2 is tidal volume, or TB. Number 3 is expiratory reserve volume, or ERV. And number 4 is residual volume, or RV. I'd like you to pause, memorize, and then resume. So, what are the four lung volumes? I stands for inspiratory reserve volume, T stands for tidal volume, E stands for expiratory reserve volume, and R stands for residual volume. Here is the 9-liter Collins tracing, wherein the x-axis is time, y-axis is volume. Upward deflection of the writing pen is inspiration, downward deflection of the writing pen is expiration. The amount of air that goes in and out of our lungs per breath, per normal relaxed breathing, is known as your tidal volume. It is known as a tidal volume because the inscription it makes in the 9-liter Collins looks like a tidal wave. Now, it has two reference points. This is at end inspiration. At end inspiration, if we are going to inspire maximally, the additional amount of air that we can inspire is logically known as your inspiratory reserve volume. Now, at end expiration, if we're going to maximally expire, the additional amount of air that we can expire logically is known as expiratory reserve volume. The amount of air remaining in our lungs after maximal expiration is known as your residual volume. So, I want you to pause, memorize this figure here, then resume once you memorize it, because that is essential in the subsequent discussion. So let's have a brief review. What is number one? It is inspiratory reserve volume. What is number two? It is tidal volume. The number three is expiratory reserve volume, and number four is residual volume. If you combine two or more lung volumes, we come out with capacities. And there are four lung capacities, and the acronym is TVIF. Okay, the first lung capacity is T, which is total lung capacity. The second one is V, as in vital capacity. Then we have the I, which is the inspiratory capacity. And then we have number 4, which is F, which is the functional residual capacity. Again, I like you to pause, memorize, and resume once you memorize it. So, what are the four lung capacities? TVIF, the first one is total lung capacity. The second one is vital capacity. The third one is inspiratory capacity. And finally, we have functional residual capacities. So I mentioned to you that if we combine two or more lung volumes, we come out with capacity. So if we combine all of the four lung volumes, that is known as your total lung capacity. If we combine the upper three lung volumes, the IRB, TV, and expiratory reserve volume, that is known as your vital capacity. If we combine the upper two, which is inspiratory reserve volume and tidal volume, that is inspiratory capacity. And when we combine the lower two, which is ERB and RB, that is functional residual capacity. So I want you to pause, memorize, and resume once you memorize this figure. So there are four lung capacities. The mnemonics is TVIF. The total lung capacity, which is composed of the four lung volumes, which is I, T, E, and R. Then you have your vital capacity, which is composed of your three upper lung volumes, which is I, T, and E. Then you have your inspiratory capacity, or IC, which is composed of your two upper, which is I and T. And you have your functional residual capacity, or your FRC, which is composed of your two lower, which is E and R. So again, I'd like you to pause, memorize, then resume. Okay, so let us combine what we have discussed so far. You have four lung volumes, which is ITER, and you have four lung capacities, which is TVIF. Okay, T stands for total lung capacity, which contains the four lung volumes, I, T, E, and R. V stands for vital capacity, which contains the three upper lung volumes, I stands for inspiratory capacity, which contains the two upper lung volumes, and F stands for functional residual capacity, which contains the ERB and residual volume. Again, I want you to pause, memorize, and resume. So we go back to this third interactive question. Which of the following is equal to FRC? Okay, what is our mnemonics? ITER and TVIF. And we're supposed to have a mental picture of this one. Okay, so if we combine IRB and TV, that is inspiratory capacity, this is pulse, ERB and RB, ERB and RB, that's functional residual capacity, that's right. So TLC minus vital capacity, TLC minus vital capacity, so it's residual volume, this is pulse. VC minus IC, VC minus IC, so that is ERB, this is pulse. So the correct answer is B, functional residual capacity is equal to ERB plus RV. So we move on to the next topic, which is elastance and compliance. So the fourth interactive question asks us which of the following is equal to the difference between alveolar and atmospheric pressures. Okay, A, transpulmonary pressure, B, trans-airway pressure, C, trans-chest wall pressure, and D, trans-respiratory pressure. So I want you to do is pause, try to answer, and resume once you have an answer. So here are the four compartment pressures in the respiratory airway. So we start off with the airway opening pressure. Okay, then we have the alveolar pressure. Then we have the pressure inside the pleura, which is pleural pressure. Then we have the atmospheric pressure. Okay, again, pause, memorize, and resume the video once you memorize the four compartment pressures. So what are the four compartment pressure? The first one is airway opening. The second one is alveolar pressure. The third one is intrapleural pressure. And the last one is atmospheric pressure. So this is another way looking at it. So this is the chest wall. This is the lung wall. And in between that is the pleural cavity. Okay, so that's the mouth opening. Okay, that's the lungs. That's the chest wall. So what are the four pressures? The compartment pressures. Okay, we have the airway opening. Then we have the alveolar pressure. Then we have the pleural pressure. Then finally, we have the atmospheric pressure. Now, what are the four trans pressure? Okay, first one is the trans airway pressure. Second one is the trans pulmonary or trans lung pressure. Third one is the trans chest wall or trans thoracic pressure. And the fourth one is the trans respiratory pressure. Okay, so for the ease of memorization for this lecture, let's just memorize the trans airway pressure, the trans pulmonary pressure, the trans chest wall pressure, and finally the trans respiratory pressure. So again, try to pause, memorize, and resume the video once you memorize these four trans pressure. The trans pressure is the pressure difference between two compartments. Okay, and therefore the trans airway pressure represents the pressure difference between the airway opening and the alveolar pressure. The transpulmonary pressure, on the other hand, represents the difference in pressure between the alveolar pressure and the intrapleural pressure. The trans-chest wall pressure represents the difference between the intrapleural pressure and the atmospheric pressure, while the trans-airway pressure represents the difference between the alveolar and the atmospheric pressure. Again, pause, memorize, and resume. So this is another way of looking at the trans pressure. Okay, what are the four trans pressure? It is the trans airway pressure. Then you have your trans pulmonary pressure. Then you have your trans chest wall pressure. Then finally you have your trans respiratory system pressure. So the trans airway pressure is the difference between the airway opening and the alveolar pressure. The transpulmonary pressure, the trans-lung pressure, is the difference between the alveolar pressure and the intrapleural pressure. Okay? The trans-chest wall pressure is the difference between the intrapleural pressure and the atmospheric pressure, while the trans-respiratory system pressure is the difference between the alveolar pressure and now the atmospheric pressure. So what is the significance of these trans pressures? These trans pressures represent the elastic property of the different organs that comprise the respiratory system. Okay? The transpulmonary pressure, which is the difference between the alveolar and the intrapleural pressure, represents the elastic property of the lungs. The transthoracic pressure, as you guess, represents the elastic property of the chest wall, while the transrespiratory pressure represents the combined elastic property of both the lungs and the chest wall. Now, if the trans pressure is positive, okay, it means that the organ has a natural tendency to contract. Again, if the trans pressure is positive, it means that the elastic property of that particular organ, it wants to contract. If the trans pressure is negative, okay, the elastic property of that particular organ is it wants to expand. Okay? So, pag positive, sobra na, gusto kong mag-contract. Pag negative, kulang pa, gusto kong mag-expand. So, which of the following is equal to the difference between the alveolar and the atmospheric pressure? A. Transpulmonary pressure. That's false because that's the difference between the alveolar and the pleural cavity pressure. The trans-airway pressure, that is false because that is the difference between the airway opening and the alveolar pressure. C. The trans-chest wall pressure, that's another false because that's the difference between the pleural pressure and the atmospheric pressure. And finally, we have the trans-respiratory pressure, which represents the difference between alveolar and atmospheric pressure. Moving on to the PIP interactive question, which of the following statements best describe the elastic property of the respiratory system? At FRC, the lungs have a natural tendency to expand. B. The chest wall has a natural tendency to contract. C. The respiratory system is most compliant. And D. The respiratory system is most elastic. So again, pause, try to answer the question, and resume your viewing once you have a tentative answer. Compliance is the tolerance to deformation. And when we talk about lung compliance, it is the inflatability of the lungs. Compliance is computed as a change in volume over the change in pressure. The mnemonic is CVP or central venous pressure. Compliance is computed as a change in volume over a change in pressure. Elastance is the tendency to recoil back to its original configuration. When we particularly talk about lung elastance, we're talking about resistance to deformation or the collapsibility of the lungs. Since it is a reciprocal term of compliance, elastance is computed as a change in pressure over a change in volume. So compliance is the tolerance to deformation. And as far as the lung is concerned, it is inflatability. So for the computation of compliance, it's CVP. Compliance is equal to the change in volume over the change in pressure. Elastance, on the other hand, is resistance to deformation. Or when we particularly talk about lung elastance, we're talking about the lungs collapsibility. So it is computed as change in pressure over the change in volume. So again, kindly pause, memorize, and resume. Now let us discuss the origin of the lung elastance or its collapsibility. Okay, one-third of the elastic property of the lungs is due to its elastic tissue content, while two-thirds is due to the surface tension. Now, what is surface tension? The lungs is composed of millions of alveoli, which behaves as a water bubble. Okay, it is lined by a layer of water molecules. Once these water molecules are exposed to air, okay, they tend to attract each other and they develop surface tension. Now, this surface tension of the lungs is kept low by the surfactant released by your pneumocytes type 2. Okay, so what will happen if the surfactant is going to be low? Okay, if the surfactant is going to be low, there's nothing to counteract the surface tension. Okay, and therefore the lung elastic property will be greater. Now let us now conceptualize elastance compliance with the pressure volume loop or line. In the x-axis is pleural pressure and the y-axis is volume. Now during this part of the loop, what is happening is the pleural pressure is made more negative and air goes into the lungs. Simultaneously, we measure pressure and the volume. Now, in this part of the pressure volume loop, the pleural pressure is made less negative and air goes out of the lungs. Simultaneously, pressure and volume are measured. Now, the difference between the inspiratory part of the loop and the expiratory part of the loop is known as your hysteresis. And this is due to the surface tension. Now, this is known as your pressure volume loop or line. And depending on what mechanical property of the lungs you're talking about, okay, it may be known as your compliance loop or line or the elastance loop or line. Now, let us now go to the measurement of lung compliance or the inflatability. So as mentioned, compliance is computed as change in volume over the change in pressure. So let us compute for the compliance of this black lung here. So the change in pressure is from 5 to 7.5. So the change is 2.5. And the change in volume is from 0 to 500. So that is roughly around 500. So 500 over 2.5, that's 200 mils per centimeter of water. Now, let us measure the compliance of this red lung here. Notice that the compliance is shifted to the right, and notice that the slope is less steep. Okay, so the change in pressure is also 2.5. However, the change in volume is around 250 ml. Okay, so when we compute for the compliance, okay, it went down to 100 ml per centimeters water. So meaning to say, a right shift or a less steep or a flat compliance line means that there's a lower compliance. Now, here's a situation wherein there's a shifting of the compliance line. This is normal, this is pulmonary fibrosis, and this is emphysema. In a healthy lung, the compliance line is at the normal position. It is a normal slope and therefore with a normal compliance. For a patient with pulmonary fibrosis, notice that it is shifted to the right. There's less steep slope, meaning to say that the lungs are less compliant. And therefore, a patient with pulmonary fibrosis will have difficulty inspiring. Now, on the other hand, a patient with emphysema, okay, you can see that the compliance line is shifted to the left. It has a steeper slope, meaning to say that the lungs are more compliant. It is easier for the patient to inspire However, since the reciprocal term for compliance is elastan, it means that the lungs are less elastic, less collapsible, and therefore patient with pulmonary emphysema is going to have a hard time expiring air. Now let's discuss elastance without surface tension. Here's the compliance loop of a lung that is air-filled, while this is the compliance loop of a lung which is saline-filled. Okay, notice that in the compliance loop of the lung, which is air-filled, there's a difference between inspiratory and expiratory part of the loop, which is known as hysteresis. And this is due to the air and water interaction, which gives rise to surface tension. Now, in the saline-filled lungs, okay, you can see that there's the loss of hysteresis. It is shifted to the left and it is steeper, meaning to say that the lungs are more compliant, less elastic, and this is due to the loss of water tension, surface tension I mean. The loss of the surface tension is on the other hand due to the loss of the air-water interaction, which is responsible for the surface tension. Okay, let's move on to some nosebleed topics, which is the elastic properties of the lungs and the chest wall. Let us now discuss the compliance of the respiratory system. Shown in this slide are three relationships, wherein the x-axis is trans-pressure, which could either be transpulmonary, trans-chest wall, or trans-respiratory system, in relationship to the y-axis, which is volume as a percentage of vital capacity. This is the compliance line of the lungs. This is the compliance line of the chest wall. And this is the compliance line of the respiratory system. We're going to divide the compliance line of the respiratory system into three parts. The first part is from 0 to 25%. Then the second part will be from 25 to 75%. And the third part will be 75 to 100%. So we end up with this figure here. So this is the compliance line of the respiratory system. We're going to represent this portion from 0 to 25% by drawing a straight line. This portion here from 25 to 75 by drawing another straight line. And from 75 to 100% by drawing another straight line here. Now this one is near FRC. The red one is near residual volume, while the blue one is near TLC. Now make a visual inspection of the three lines. The steepest, as you can see, is the green one, which is near FRC, meaning to say that the respiratory system is most compliant near FRC. And when we compare near RB to near FRC, the red line is less steep and therefore it is less compliant compared to that of near FRC. The same can be said about that line near TLC. The slope is less and therefore near TLC, the respiratory system is less compliant compared to that of near FRC. So what I'm saying is the compliance of the respiratory system is a triphasic manifestation. It is less compliant from 0 to 25%, becoming more compliant from 25 to 75%, then again less compliant from 75 to 100%. So this is another way of looking at it, now in relationship to the pore lung volumes and functional residual capacity. Okay, it is less compliant near RB, becoming more compliant near FRC, and again becoming less compliant near TLC. So where do we do our tidal breathing? We do our tidal breathing, okay, above FRC, where the respiratory system is most compliant, and therefore it is easier to inflate the lungs, and therefore the work of breathing is less. So let us review what we have discussed so far with regards to the slope and shifting of the compliance curve. A right shape of the curve means that the lung is less compliant. A lower slope of the line means that the lung is less compliant, and near RB and near TLC, okay, the respiratory system is less compliant. So let us now go back again to the significance of the thrust pressure. The transpulmonary pressure will reflect the elastic property of the lungs. The transthoracic pressure will reflect the elastic property of the chest wall, and the transrespiratory system pressure will reflect the elastic property of the respiratory system. I mentioned if the trans pressure is positive, the elastic property of that organ is to contract, while if the trans pressure is negative, the elastic property of that organ is to expand. So let us now discuss the elastic property of the chest wall. Since we're talking about the chest wall, the x-axis will be the trans chest wall pressure, okay, while the y-axis will be percent of the vital capacity. Now let us remember that if the trans chest wall pressure is positive, the elastic tendency of the chest wall is to contract, while if it is negative, the elastic property of the chest wall is to expand. Now, this is the elastic line of the chest wall. Let us determine now what is the trans chest wall pressure at 0% of the vital capacity. So it's negative 38. At 30%, it's negative 5. At 60%, it is 0. And at 100%, it is positive 7. Notice that from a lung volume of 0 to 60% of the vital capacity, the trans chest wall pressure is negative, and therefore the elastic tendency of the chest wall is to expand. At 60% of the vital capacity, the trans chest wall pressure is 0, and therefore the chest wall neither wants to expand nor contract. Beyond 60%, the trans chest wall pressure is positive, and therefore the elastic tendency of the chest wall is to collapse. So basically, the chest wall has a biphasic elastic tendency, and the inflection point will be at 60% of the vital capacity. So, the trans chest wall pressure of 0 is at 60% of the vital capacity. So the magic number, as far as the elastic tendency of the chest wall is concerned, it is 60%. Okay? It has a biphasic elastic tendency. Below 60%, it wants to expand, while above 60%, it wants to contract. So let us now discuss the elastic property of the lungs. Since we're talking about the lungs, the x-axis will be your transpulmonary pressure, while the y-axis is still percent of the vital capacity. Again, if the transpulmonary pressure is positive, the lungs have a natural tendency to contract, while if it is negative, the lungs have an elastic tendency to expand. Now, this is the elastic line of the lungs. At 0% of the vital capacity, the transpulmonary pressure is positive 3. At 30, it's positive 5. And at 60%, it's positive 10. And at 100%, it is plus 30. Notice that from 0% of the vital capacity till 100% of the vital capacity, the transpulmonary pressure is positive, and therefore the lungs have an elastic tendency to contract from 0 to 100% of the vital capacity. So basically, the lungs have a monophasic elastic tendency. It always wants to contract. Okay, so the transpulmonary pressure of 0 is not seen in the elastic line of the lungs, and therefore the magic number is 0% of the vital capacity. Okay, above 0% of the vital capacity, the lungs have a natural tendency to contract. So the lung has a monophasic elastic property. Okay, it as much as possible, it wants to contract. Now let us try to analyze the relationship between the elastic property of the lungs and that of lung volume. So this is the elastic line of the lungs. As you can see, the greater the lung volume is, the greater is the transpulmonary pressure. The greater the transpulmonary pressure, the greater is the elastance, the greater is the collapsibility of the lung, and the greater is the resistance to deformation or inflammation. So, putting it in another way, the greater the lung volume, the greater the transpulmonary pressure, the greater the elastance, the greater the collapsibility, the greater is the resistance to inflation. Now, from a nosebleed topic, let us move to a topic which will make you vomit, and that is the elastic property of the respiratory system. Moving on to the elastic property of the respiratory system. Now, the x-axis will be your transrespiratory pressure. Again, if it is positive, the respiratory system has an elastic tendency to contract, while if it is negative, it has an elastic tendency to expand. Again, the y-axis is still percent of the vital capacity, and this is the elastic line of the respiratory system. And at 0% of the vital capacity, the transrespiratory pressure is negative 35. At 30%, it is 0. At 60%, it is plus 10. And at 100%, it is plus 37. Notice that the transrespiratory pressure from 0 to 30% of the vital capacity is negative, and therefore, the respiratory system has an elastic tendency to expand. At 30% of the vital capacity, or a functional residual capacity, the transrespiratory pressure is 0, meaning to say it doesn't want to expand nor contract. Beyond 30% or beyond FRC, the transrespiratory pressure is positive, and therefore the respiratory system has an elastic tendency to collapse. And therefore, just like the chest wall, the respiratory system has a biphasic elastic tendency. But this time, the inflection point is not 60%, but at 30% of the vital capacity, or at FRC. So the transpulmonary pressure of 0 is achieved at 30% of the vital capacity, or FRC. So when we talk about elastic property of the respiratory system, the magic number is 30% of the vital capacity, or FRC. Below FRC, the respiratory system has an elastic tendency to expand, while above FRC, the respiratory system has an elastic tendency to contract. And therefore, the respiratory system has a biphasic elastic tendency, and the inflection point is at FRC. So let us review what we have been discussing for the past 10 minutes. What is the elastic property of the chest wall, the lungs, and the respiratory system? This is the figure which we've been trying to analyze. In the x-axis is the transmural pressure, and the y-axis is lung volume, this time represented as percent of the TLC. The green one is the elastic line of the chest wall, the red one is the elastic line of the lungs, and the black one is the elastic line of the respiratory system. In this figure here, the green arrow would represent the elastic property of the chest wall, while the red arrow would represent the elastic property of the lungs. So here is a tabular graph which represents this figure over here. Okay, at 100% of the vital capacity, the trans-chest wall pressure is positive 7, and therefore it wants to contract. The trans-lung pressure is positive 30, and therefore the lungs would like to contract. If the transrespiratory pressure, which is the sum of plus 7 plus 30, is positive 37, and therefore it wants to contract. Okay, so at 100% of the vital capacity, the chest wall has an elastic tendency to contract, just like the lungs has an elastic tendency to contract. So, at 100% of the vital capacity, it is plus 7 for the trans-chest wall, it is plus 30 for the transpulmonary pressure, and therefore if you sum this both up, it is plus 37 for the respiratory system. Now, at 60% of the vital capacity, the trans-chest wall pressure is 0 and therefore it is neutral. The transpulmonary pressure is plus 9 and therefore it wants to contract. And therefore, if you add 0 plus 9, it is equal to plus 9 and therefore the respiratory system elastic pressure is plus 9. It wants to contract. So at 60% of the vital capacity, the chest wall neither wants to expand nor contract, while the lungs would like to contract. At 60% of the vital capacity, okay, the trans-chest wall pressure is 0. The lungs transpulmonary pressure is plus 9, and therefore the respiratory system wants to contract. Now, the most important one is at 30% of the vital capacity, or the FRC. Notice at FRC, the trans-chest wall pressure is negative 5, it wants to expand, while the transpulmonary pressure is plus 5, it wants to contract. And therefore, when we add it both up, it's 0, and therefore the respiratory system trans pressure is 0 and it's neutral. It neither wants to expand nor contract. So this is the representation on the elastic property of the respiratory system at functional residual capacity. The lungs would like to expand, the chest wall would like to contract, they equalize each other, and therefore the transrespiratory pressure is 0. So the lungs would like to contract, okay, the chest wall would like to expand, and therefore they equalize each other, the transrespiratory pressure is 0. So the respiratory system would neither like to contract nor expand. Then at 0% of the vital capacity, the trans-chest wall pressure is negative 38, so the chest wall would like to expand. And the transpulmonary pressure is plus 3, and therefore the lungs would like to contract. And when we add it both up, that's a negative 35, so the respiratory system has an elastic tendency to expand at 0% of the vital capacity. Okay, so at 0% of the vital capacity, the chest wall would like to expand, while the lungs would like to contract. Okay, so the chest wall would like to expand, while the lungs would like to contract. This is more powerful than this one, and therefore the respiratory system would like to expand. So let us summarize things at this point. With regards to compliance of the respiratory system, it is most compliant at FRC and least compliant at RB and TLC. With regards to elastic tendency is concerned, the lungs have a monophasic elastic tendency. As much as possible, it wants to contract or collapse. The chest wall, on the other hand, the elastic property is biphasic, and the inflection point is 60%. At greater than 60%, it wants to contract, and less than 60%, it wants to contract. The respiratory system has likewise the same biphasic elastic tendency, and the inflection point is now at 30% or at FRC. Okay, above 30%, it wants to contract, and below 30%, it wants to expand. Okay, did you survive that? Are you still alive? Okay, let's move on to the next one. What is the origin of the negative intrapleural pressure? Now at FRC, you can see here that the chest wall would like to expand and the lungs would like to contract. And therefore, these opposing elastic properties, a negative intrapleural pressure is generated. So what is the significance of our FRC? The FRC is known as your relaxed lung volume. It is the lung volume or the capacity wherein the elastic property of the chest wall and the lungs equalize each other. It is the relaxed lung volume which the respiratory system will try to maintain if the respiratory muscles are relaxing. Okay, so therefore, if we inspire maximally up to TLC and we relax our inspiratory muscle, on its own, the respiratory system will go back to FRC, even without us using our expiratory muscle. If we expire maximally down to RB and relax our expiratory muscle on its own because of the elastic property of the respiratory system, we'll go back to FRC. And this is the basis why expiration is a passive process. So when we inspire, when we inhale our tidal volume, we contract our inspiratory muscle, and when we expire, we just relax our inspiratory muscle, and on its own, it is going to go back to FRC. So let's go back to this interactive question number 5. Which of the following statements best describe the elastic property of the respiratory system? At FRC, the lungs have a natural tendency to expand. That's wrong. It wants to contract. The chest wall has a natural tendency to contract. That's again false. It wants to expand. The respiratory system is most compliant. Okay, that's right. And the respiratory system is most elastic. And that's false. So the correct answer is the respiratory system is most compliant. So let us summarize things at this point. There are four lung volumes. The mnemonics is ITER, and there are four lung capacities. It's TBIF. With regards elastance is concerned, it is resistance to deformation, or as far as the lungs is concerned, it's collapsibility. It is due to 1/3 elastin content and 2/3 due to surface tension. Compliance, on the other hand, is the tolerance to deformation or the inflatability as far as the lungs are concerned. It is computed as central venous pressure, its volume over pressure. It is plotted by the pressure-volume loop or line. A right shift means that there is a decreased compliance. A decrease in slope means that there's a decrease in compliance. There are four compartment pressures and four trans pressure. The trans pressure would represent the elastic property of a particular organ. If it is positive, it has an elastic tendency to contract, while if it is negative, it has an elastic tendency to expand. The lungs have a monophasic elastic tendency. It always wants to collapse. The greater the lung volume, the greater is the elastic tendency. A biphasic elastic tendency is both seen in the chest wall and the respiratory system. The inflection point for the chest wall is 60% of the vital capacity, while that for the respiratory system is 30% of the vital capacity, or at FRC. The FRC has a lot of physiologic significance. The elastic recoil of the lung and the chest wall balances each other. It is known as the relaxed lung volume or capacity. It is the configuration which the respiratory system will maintain if all of the muscles, respiratory muscles, are relaxed. It is the basis while expiration is a passive process during normal quiet breathing. Let's move on to the fourth topic, which is the mechanics of breathing. The sixth interactive question asks us the alveolar pressure is most negative at which part of the tidal breathing? A. Start of inspiration. B. Mid-inspiration. C. End of inspiration. D. Mid-expiration. So I want you to pause, try to answer, and resume the video once you have a tentative answer. Let us now discuss the changes during tidal breathing. Okay, at FRC, the alveolar pressure is 0 relative to the atmosphere, and therefore there is no flow of air. During inspiration, the brain is going to command the chest wall to expand. Expansion of the chest wall is going to make the alveolar pressure negative relative to the atmosphere. Since air moves from greater pressure to lesser pressure, air will move in. During expiration, the brain is going to command the inspiratory muscle to relax. Relaxation of the inspiratory muscle will cause contraction of the thoracic cage. This is going to make the alveolar pressure positive relative to the atmosphere, and therefore this will cause air to move out into the atmosphere. So what I'm driving at is that the alveolar pressure, this one, is the one that drives air to flow in and out of the lungs. Now, let us discuss the changes during tidal breathing. The first thing that's going to change is the pleural pressure, followed by the alveolar pressure. Then there will be flow of air. Then finally, there will be increase in lung volume. Okay. At FRC, this is our resting lung volume. The intrapleural pressure is -5. the alveolar pressure is equal to the airway opening pressure. That's why there's no flow of air. Now, during inspiration, the inspiratory muscle is going to contract. This is going to increase the pleural cavity volume. The increase in pleural cavity volume is going to decrease the intrapleural pressure, and this will make the intrapleural pressure more negative. So the intrapleural pressure becomes more negative, and this is transmitted to the alveolar pressure. It gradually becomes negative, and this will cause an inspiratory flow of air. This is going to increase the lung volume. The pleural pressure negativity progresses and peaks at the end of inspiration. The negativity of the alveolar pressure peaks at mid-inspiration and gradually returns to zero at end inspiration. Inspiratory flow peaks at mid-inspiration and gradually returns to zero at end inspiration. And lung volume further increase and peaks at end inspiration. During expiration, the inspiratory muscle is going to relax. The lung is going to recoil back to FRC, and this will cause a diminution in volume and therefore an increase in pressure. This increase in pressure will cause less negativity of the intrapleural pressure. And therefore the pleural pressure becomes less negative. The alveolar pressure becomes positive. The expiratory flow starts occurring and the lung volume starts decreasing. The pleural pressure negativity progressively decreases back as it level in FRC. The positivity of the alveolar pressure peaks at mid-expiration and gradually returns to zero at end expiration. The same goes with expiratory flow. It peaks at mid-inspiration and gradually returns to end expiration, and the lung volume further decreases back to baseline, which is functional residual capacity. So these are the changes during tidal breathing. As far as the pleural pressure is concerned, it assumes a U wave. The alveolar pressure assumes a sine wave. Since the alveolar pressure is the driving pressure per flow, the flow likewise assumes a sine wave, while that of volume assumes an inverted U wave. So the pleural pressure is most negative at the end of inspiration. The alveolar pressure is zero at end inspiration and end expiration. It is most negative during mid-inspiration and most positive during mid-expiration. Okay. The flow is zero at end inspiration and end expiration, and it is fastest during mid-inspiration and mid-expiration. And the volume is highest at end inspiration. So let us now discuss the respiratory cycle time and the IE ratio. In the x-axis is time, in the y-axis is volume. Now this is the inspiratory part of the respiratory cycle, and it is composed of three phases. There's inspiration, then there's expiration, then finally there's a period of no flow, which is known as apnea phase. So the period of the respiratory cycle is divided basically into inspiration and expiration. Expiration includes the expiration proper and the apnea phase. Now, this is the total time for one respiratory cycle. And when we try to see the ratio of the inspiratory time and the expiratory time, we can see that normally, okay, the IE ratio is 1:2 to 3, meaning to say expiration is 2 to 3 times longer than that of inspiration. When we increase our respiratory rate, the respiratory cycle time decreases, the inspiratory time decreases, but the expiratory time decreases more, and therefore the IE ratio becomes bigger, so it becomes 1:1:2. So we go back to this interactive question. The alveolar pressure is most negative at which part of the tidal breathing? Start of inspiration, that is pulse, because it is zero. During mid-inspiration, that's the correct answer. At the end of inspiration, No, the alveolar pressure is 0 at the end of inspiration during mid-expiration. No, it is most positive during expiration. So B is the correct answer. Now let us move on to the fifth topic, which is airway resistance. So which of the following causes a turbulent airflow pattern? A. Low gas density. B. Slow airflow velocity. C. A low Reynolds number. D. A large luminar airway diameter. So again, I like you to pause, try to answer, and resume. For number 8, it asks us which of the following is accurate with regards to small airway resistance. A. It contributes highest to total airway resistance. B. Highest at TLC. C. Not dependent on bronchial smooth muscle contraction. And D. Inversely related with lung elastance. Again, I like you to pause, try to answer, then resume. The airway resistance is the frictional hindrance to the flow offered by the air passages. It is governed by Ohm's law, which states that flow is directly related to driving pressure while inversely related to airway resistance. And therefore, the higher the airway resistance, the lower will be the flow of air. The resistance offered by the airway depends on two factors. One, the type of flow pattern, and two, the physical attributes of the airways and the gas, which is governed by Passow's law. The airway is divided by the larynx into your upper airway and to your lower airway. The lower airway is actually just the trachea undergoing 23 dichotomous branching ending up with millions of your alveoli. The lower airway can be divided further into your respiratory zone, that is from airway generation 17 to 23. The structures are with alveoli and therefore there's gas exchange. That's why this is known as your respiratory zone. While airway generation 1 to 6, they're devoid of alveoli and therefore they're known as the conducting zone because their main job is just to conduct air from the upper airway down into the respiratory zone. Okay, the conducting zone is further divided into your large airways and the small airways. Small airways anatomically are those with less than 2 millimeters in diameter. They are known as your bronchioles and they're devoid of cartilages. They are from airway generation 10 to the 16th. Now, let us discuss the airflow pattern. The airflow pattern in the upper airway and the conducting zone is by bulk flow, and that on the respiratory zone, it is a much lower, the diffusion type of airflow pattern, because that is where the gas exchange occur. The bulk flow can be further divided into your laminar, turbulent, and transitional. So there are three types of flow pattern: the laminar, the turbulent, and the transitional. What will determine what will be the flow pattern will be your Reynolds number. Reynolds number is directly related to the density, velocity of airflow, the diameter of the conduit, and the viscosity of the gases. Okay, the way to memorize this is Rn is equal to dBd over vis. So density, velocity, diameter over viscosity. So this one is the confusing part, but the way to memorize it, it is alphabetical. It is velocity over viscosity. Now the turbulent flow pattern is assumed if the Reynolds number is greater than 2000. The turbulent pattern offers a higher resistance compared to that of a laminar pattern. The turbulent pattern is primarily seen in the trachea because the velocity of airflow in the trachea is very high and likewise the diameter of the trachea is very large and therefore the Reynolds number will be high, more than 2000, causing a turbulent airflow pattern. The laminar pattern occurs if the Reynolds number is less than 1000. It offers a lower resistance compared to the turbulent pattern and it occurs primarily in the small airways or in the bronchioles. This is so because the velocity of airflow in the small airways is low and likewise the diameter of the bronchioles is likewise small, and therefore the Reynolds number will be less than 1000 and the flow will be laminar. If the Reynolds number is between 1000 to 2000, it is going to assume a transitional type of airflow pattern. So the ball flow that occurs in the conducting zone can assume three patterns. Okay, in the large airways, it is a turbulent flow pattern. In the small airways, it is a laminar flow pattern, and somewhere in between is the transitional flow pattern. Another thing that will determine the airway resistance are the physical attributes of the airways and the gas, which is governed by Passow's law. It states that airway resistance is directly related to the viscosity of the gas, the length of the tube, and the radius of the airways. The airway's radius is dependent on its mucosal thickness, the smooth muscle tone, and the tethering effect of the lung parenchyma. The large airways radius is dependent on the mucosal thickness and the contraction and relaxation of the bronchial smooth muscle. The small airways or the bronchioles are devoid of cartilages. They're likewise dependent on the mucosal thickness, the smooth muscle tone, but likewise they are dependent on the tethering effect of the surrounding lung parenchyma. So this is an example of the tethering effect of the surrounding lung parenchyma. They're devoid of cartilages, so they tend to collapse. And what keeps them patent is the elastic pull of the surrounding lung parenchyma. Let us now discuss the small airways resistance and its relationship with that of lung volume. I want you to go back to this slide which we discussed with regards elastance is concerned. And based on this diagram, we discussed that the greater the lung volume, the greater the transpulmonary pressure, the greater is the lung elastance. Okay? So, small airways resistance and its relationship with the lung volume. Okay, the small airways is dependent on the tethering effect of the surrounding lung parenchyma. What will determine the tethering effect is the elastance of the lungs. Okay, at residual volume, there's low lung elastance and therefore the tethering effect is small and therefore the radius is likewise small. At TLC, since the greater the lung volume, the greater the elastance, we have a higher lung elastance and therefore there's a greater pull of the small airways and therefore the radius is much greater compared to that of residual volume. And therefore, the greater the lung volume, the greater the lung elastance or the tethering effect, the greater is the radius, the smaller is the small airway resistance. So that relationship is shown by this graph, okay, wherein the x-axis is volume and the y-axis is airway resistance. Notice that the airway resistance is inversely related. Okay, the greater the lung volume, the lower is the airway resistance. So let us now discuss the distribution of the total airway resistance. 50% of the total airway resistance is contributed by the nose. 30% is contributed by the large airways and the pharynx, while only 20% is contributed by the bronchioles. Let us now compare the resistance offered by all of the large airways compared to that of the small airways. Okay, based on Passow's law, which states that the radius is inversely related to airway resistance, we expect that the airway resistance offered by the small airways will be much larger, much bigger compared to the large airways. Here is a graph which will try to answer to us which offers a greater airway resistance, the large or the small airways. So in the x-axis is the trachea, the bronchus, and the bronchioles, and the y-axis is the resistance offered. Notice, contrary to our expectation, okay, the more distal or smaller airways offer less resistance. Why is this so? Okay, if we get the radius of the trachea, probably it is just this big. Okay, if we get the radius of all of the bronchioles, because there are numerous bronchioles, we can see that the total luminal radius of all of the bronchioles is much larger, and therefore the resistance offered by all of the bronchioles is lower compared to that of the trachea. So we go back to this interactive question: which of the following causes a turbulent airflow pattern? So what equation do we need? Okay, it is the Reynolds number. And Reynolds number, what's our formula? It is dBd over d, that is velocity over viscosity. Okay, so low gas density, that's false. The lower the density, the lower the Reynolds number. We want a high Reynolds number because we're talking about turbulent flow. Slow airflow velocity, again, that is false. Low Reynolds number, again, we want a high Reynolds number. A large luminal airway diameter. So if the diameter will go up, the Reynolds number will go up, and that is the correct answer. So for number 7, a large luminal airway diameter is the correct answer. For number 8, which of the following is accurate with regards small airway resistance? Contributes highest to the total airway resistance, that's false. It is the nose. Highest at TLC, that is false because it's inversely related. The greater the lung volume, the higher the elastance, the greater the tethering effect, the greater the small airway radius, the lower is the airway resistance. It is not dependent on bronchial smooth muscle contraction. Both the large and the small airways are dependent on bronchial smooth muscle contraction, inversely related to lung elastance. That's the correct answer. The greater the elastance, the greater the radius, the smaller is the airway resistance. Let us now move on to the 6th topic, which is the distribution of ventilation. Which of the following most accurately describe inhalation from RB to TLC? The bases are better ventilated from RB to FRC. The apices are better ventilated from FRC to TLC. At RB, the lower lung zones are more compliant than the upper lung zones. And D, at FRC, the lower lung zones are more compliant than the upper lung zone. Again, I'd like you to pause, try to answer, and then resume. So what are the factors that will determine the respiratory unit's ventilation? The greater the resistance, okay, the lower is the ventilation. The greater the compliance, okay, the greater the compliance, the higher is the ventilation. And therefore, the greater the compliance, the greater the ventilation, the greater the resistance, the lower the ventilation. Between the two, what will determine the distribution of ventilation under normal condition is compliance. Again, let us have a brief review. A right shift of the compliance curve means that it is less compliant. The lower the slope, the less compliant is. Near RB and TLC, the respiratory system or the lungs is less compliant. Now let's compare the compliance of the lung versus that of the alveolus. The lungs as an organ is less compliant near RB and TLC against that of FRC. It is, however, composed of several alveoli. It is wrong to say that the alveoli of the lung at RB are less compliant than the alveoli of the lung at FRC because there's a regional alveoli compliance differences in the different lung zones. What will determine the compliance of the alveolus is its size. The alveolus size may vary from almost collapsed, moderately distended, or maximally distended. Okay. If we try to determine the compliance loop on almost collapsed alveoli and inflate it, okay, till maximally distended, we're going to have the same compliance loop as that of the lungs. Okay, as you can see here, it is most compliant, the alveolus is most compliant when it is moderately distended. Now, what are the factors that will determine the configuration of the alveolus? Whether it's going to be almost collapsed, moderately distended, or maximally distended. The factors that will determine the configuration of the alveolus are the differences in the pressure inside and outside the alveolus. The inside pressure is the alveolar pressure, and the outside pressure is the intrapleural pressure. And we know that the difference between the alveolar and the intrapleural pressure is known as your transpulmonary pressure. This is the distending pressure of the alveolus. Let us now examine the configuration of the alveoli in an upright lung. The alveolar pressure is not affected by gravity, so it's zero throughout from upper to lower lung zone. The intrapleural pressure, on the other hand, is affected by gravity. It is most negative at the apices and least negative at the bases. And therefore, if we try to compute for the transpulmonary pressure, which is the difference between the alveolar and intrapleural pressure, 0 minus minus 10 is plus 10, 0 minus minus 2 is plus 2. We can see that due to the effect of gravity, the transpulmonary pressure is more positive in the upper lung zones compared to the lower lung zones. And because of this, okay, the upper lung zones alveoli are more distended than the lower lung zones alveoli. So let's now analyze the regional lung compliance at residual lung volume. So if this is the lung, okay, this is the configuration of the alveoli. Okay, notice at the bases, the alveoli at RB, okay, are almost collapsed, so it's less compliant. While at the apices, it is moderately distended and therefore more compliant. And therefore, when we are going to inhale from RB to FRC, most of the ventilation is going where? When we inhale from RB to FRC, which is better ventilated. Better ventilated are the moderately distended, and therefore, when we inhale from RB to FRC, the upper lung zone is better ventilated than the lower lung zone. Now, let us examine now the regional compliance, deep compliance of at functional residual capacity. At FRC, you can see at the bases, okay, the alveoli are moderately distended, while the superior portal alveoli are fully distended. And therefore, at FRC, the lower lung zones alveoli are more compliant than the upper lung zones. So if we're going to inhale from FRC to TLC, we're going to inhale from FRC to TLC, which is better ventilated. Of course, which is going to be better ventilated? The one that is more compliant, which is moderately distended at the bases. So the lower lung zones is better ventilated as we inhale from FRC to TLC. So where do we do our tidal breathing? We do our tidal breathing above FRC. So right now, our lung bases are better ventilated than the apices when we do tidal breathing. So this is another way of looking at it. So when we exhale down to RB and we inhale from RB to FRC, the upper is better ventilated. However, when we inhale from FRC to TLC, the lower is better ventilated. So we go back to this interactive question. Which of the following most accurately describe inhalation from FRC to TLC? The bases are better ventilated from when we inhale from RB to FRC. That's false because it is the apices. The, the apices are better ventilated from FRC to TLC. That's again wrong because we know it is the bases. At RB, the lower lung zones are more compliant than the upper lung zones. That's false. Okay, the upper lung zones are more compliant at RB. At FRC, the lower lung zones are more compliant than the upper lung zone, and that's the correct answer. So we move on to the seventh topic, which is the work of breathing. Which of the work of breathing component increases in a patient with hyaline membrane disease? A, the viscous tissue resistance. B, the airway resistance work of breathing. C, the non-elastic component. And D, the elastic component. Again, I'd like you to pause, try to answer, then resume. Let us now discuss the work of breathing. During inspiration, the inspiratory muscle is going to contract to expand the chest wall, which is composed of non-elastic tissue, and the lungs, which is composed of elastic tissue. This is going to create the necessary driving pressure for air to move in against the frictional resistance offered by the airways. During expiration, on the other hand, okay, the chest wall and the lungs possibly recoil back to FRC, and this creates the necessary driving force for air to move out of the lungs against the frictional resistance offered by the airway. So the work of breathing during inspiration can be divided into elastic work of breathing, which is the work done to expand the lungs, and we have the non-elastic work, which is composed of two components to expand the chest wall and likewise to counteract the frictional resistance offered by the airways. Let us now discuss the work of breathing during expiration. During expiration, there is no contraction of the muscles. It is the elastic recoil to FRC which generates the necessary driving force, and the expiratory muscles only contract if there is increased airway resistance. So the work of breathing could be classified as the elastic work of breathing, which is the work done to expand the lungs, which is composed of elastic tissue. The non-elastic work of breathing is composed of two components. It is the work done to expand the non-elastic tissues, which is otherwise known as the viscous resistance work of breathing. And the other component of the non-elastic work of breathing is the work done to counteract the frictional resistance of the airways to the flow of air. Now, 65% of the total work of breathing is due to the elastic work of breathing, while 7% accounts for the viscous resistance work of breathing, and airway resistance accounts for 28% of the total work of breathing. The work of breathing is measured by the pressure volume area. Okay? During inspiration, a driving pressure, as shown in this illustration, is generated from -2 to -6, so that a volume of air, as shown in this diagram, around 1 liter will go in. Now, during expiration, a driving pressure is again generated. That's from -6 to -2, so that a volume of air will move out of the lungs. The elastic work of breathing is represented by this area over here, OACDO, and the viscous resistance work of breathing is likewise embedded in this area over here. Okay, the airway resistance work of breathing, on the other hand, is represented by OECFA. This is the inspiratory part, and that's the expiratory part of the work of breathing. Okay, now under normal conditions, there's no work of breathing during expiration. It is a passive process. The passive recoil of the FRC generates the driving pressure. The work of breathing was done during inspiration to expand the respiratory system so that as to create the elastic recoil pressure necessary to expel air out during expiration. So normally, the total energy expenditure allotted for the work of breathing is only 5%, and thus it is so low that we're not aware that we are breathing. The work of breathing may be increased in pathological condition. Elastic work of breathing may be increased in lung diseases, or tissue resistance work of breathing may be increased in chest wall diseases. Examples are hyaline membrane disease, congestive heart failure, pneumonia, or scoliosis. In hyaline membrane disease, there's deficiency of the surfactant and therefore there's increased lung elastance. So what's going to happen during increased elastance is the compliance curve is going to shift to the right. The inspiratory muscle needs to contract harder from -2 to -10 or 11 to expand the less compliant respiratory system. As you can see, the area increases OACD. And likewise, there's a shift of the compliance curve to the right. Now, the airway resistance work of breathing may be increased in asthma or COPD. And you can see here that the loop becomes larger. Okay, so during inspiration, okay, the inspiratory muscle needs to generate a more negative intrapleural pressure to create a higher driving pressure for air to go inside the lungs. Now, during expiration, okay, the expiratory muscles now need to contract to counteract the frictional resistance during expiration because the elastic recoil of the lungs back to FRC is not enough to generate the necessary driving pressure to propel air out against an increased airway resistance. So we go back to this question here. Which work of breathing component increases in a patient with hyaline membrane diseases? Okay, viscous tissue resistance, no? It increases during chest wall diseases. Airway resistance, we only see that in asthma, COPD, or airways diseases. The non-elastic work of breathing, that's wrong because the non-elastic work of breathing is composed of your increased airway resistance work of breathing and likewise increased tissue resistance work of breathing. And the correct answer is the elastic work of breathing. This is usually increased in lung parenchymal diseases. So the correct answer is the elastic work of breathing. Now, so let us summarize things at this point here. With regards to the mechanics of breathing, there will be contraction of the inspiratory muscle, which is going to cause changes in the pleural pressure, alveolar pressure, so there will be airflow, and there will be increase in lung volume. Now, during expiration, there will be recoil back to FRC. The pleural pressure becomes less negative, the alveolar pressure becomes positive, causing expiratory flow and diminution in lung volume. Under normal condition, the IE ratio is 1:2:3. Okay, the lower airway is divided into your conducting zone and respiratory zone. Okay, the conducting zone is further subdivided to its large and small airways. The small airways are devoid of cartilages and therefore they're dependent on the lung elastance tethering effect. The lower airway can be divided further into conducting zone and the respiratory zone. Okay, in the conducting zone, the flow pattern is by bulk flow. And in the large airway, it is turbulent, while in the small airway, it is laminar, and somewhere in between, it is transitional. The airway resistance is dependent on the flow pattern and the physical dimensions or the radius, which is dependent on the smooth muscle tone, mucosal thickness, and the tethering effect. Now, the flow pattern is dependent on the Reynolds number, and it's dBd over bis, density, velocity, diameter over viscosity. Okay, the airway resistance is highest at the nose, followed by large and the upper airway and the large airways, and the small airways only contributes, small airway only contributes 20% of the total airway resistance. Due to the effect of gravity on pleural pressure, the upper lung zone alveoli is more distended than the lower lung zone. When we inhale from RB to FRC, the upper is better ventilated, and as we proceed from inhalation from FRC to TLC, the lower is better ventilated. The work of breathing is measured by the pressure volume area. There are three types: the elastic work of breathing, the non-elastic work of breathing, which is further subdivided into your viscous tissue resistance work of breathing, and the airway resistance work of breathing. The elastic work of breathing accounts for 65% of the total work of breathing. It is increased in lung parenchymal diseases such as in alveolar or interstitial lung diseases. The viscous tissue resistance work of breathing accounts for only 7%, and it's increased in chest wall diseases such as in pleural, neuromuscular, and thoracic cage diseases. The airway resistance work of breathing accounts for 28% and is increased in airway diseases. Under normal condition, only 5% of the total energy expenditure is used in the work of breathing. So we move on to the next topic, which is pulmonary circulation. Question number 11 reads, which of the following constrict the pulmonary arterioles? A. Oxygen, B. Nitric oxide, C. Prostaglandin, and D. Thromboxane A2. Again, I'd like you to pause, try to answer, and then resume. Number 12 reads as follows, which of the following best describe the pulmonary vascular resistance? PBR due to extra-alveolar vessels is highest at TLC. PBR due to alveolar vessels is highest at RB. Total PBR is higher in RB than FRC. And total PBR is higher in FRC than in TLC. Again, I'd like you to pause, try to answer, and then resume. Okay, this is an overview of the pulmonary and the bronchial circulation. Okay, so the bronchial artery is the branch of the aorta and supplies oxygenated blood to the airways. This is drained by the bronchial vein, which drains into the pulmonary veins. So this is one of the two anatomic shunts in our body. This is the pulmonary circulation, which is composed of your pulmonary artery, the pulmonary capillaries, and that of the veins. And when we enlarge the pulmonary capillaries, we come out with this illustration here. Okay, so this is the site of the gas exchange, the alveolo capillary membrane. Okay, it is a special design, the pulmonary capillary. It is just composed of a single endothelial cell. This is the site of the exchange of fluids, and it is governed by Starling's law. So let us discuss the fluid movement in the pulmonary microcirculation. So this is the pulmonary capillary. There are hydrostatic forces inside and outside the capillary, and there are oncotic forces both inside and outside of the capillaries. Okay, some of these forces are filtrating forces, some of them are absorbing forces. The filtration forces are your capillary hydrostatic pressure and your interstitial oncotic pressure, while the absorption forces are your interstitial hydrostatic pressure and your capillary oncotic pressure. Okay, the movement of fluid across the AC membrane or the movement of fluid across the capillary and the interstitium is governed by your Starling's equation. Starling's equation states that K stands for hydraulic conductivity times the difference between the capillary hydrostatic pressure and the interstitial hydrostatic pressure minus K sigma, which is the colloid osmotic reflection coefficient, times the difference between the oncotic pressure in the capillaries and the oncotic pressure in the interstitium. Okay, so K reflects the ease of fluid can pass through the membrane. Sigma would reflect the effectiveness of the solute in generating the osmotic driving forces. Now, if this equation, Starling's equation, is positive, it means that there's filtration. If this equation shows negative, meaning that there's absorption. Now, what is the fluid movement in the pulmonary microcirculation under normal condition? This is illustrated by this diagram here, showing to us the different interstitial and capillary hydrostatic pressure and oncotic pressure. And when we substitute those numbers here, we can see that the flux is positive. So normally, there's movement of fluid from the capillaries into the interstitium. So there's movement of fluid into the interstitium. You have a flux of 1. Now, usually, there's no fluid accumulation here because those fluid moving out of the pulmonary circulation is immediately drained by the lymphatic vessels. Okay, so normally there's a flux of fluid and the lymphatics prevent its accumulation. Okay, let us now discuss pulmonary edema. Pulmonary edema occurs if the flux is positive, is greater than the lymphatic drainage. Okay, so that may occur if there's increased capillary hydrostatic pressure, such as in left heart failure or fluid overload, or there's a decrease in your hydrostatic pressure in the interstitium, such as in re-expansion pulmonary edema, or there may be decreased oncotic pressure in the pulmonary capillaries, such as in protein-losing nephropathy, liver diseases, and malnutrition, or there may be changes in the K or the sigma. Okay, there may be increased K or a decreased sigma, which is usually secondary to inflammation. This will cause a positive flux, which may overwhelm the lymphatic drainage. So, finally, there may be lymphatic obstruction, okay, such as it may be blocked by a malignancy or by parasites such as your schistosoma, which will cause fluid accumulation in the interstitium. Okay, what are the differences between the pulmonary and the systemic circulation? Well, with regards to systemic circulation, its main function is for blood supply regulation. And the resistance is high, the pressure in the systemic circulation is high, and the response to hypoxia is vasodilation. It's different in the pulmonary circulation. The main function of the pulmonary circulation is for blood oxygenation and carbon dioxide elimination. The resistance is low and the pressure is likewise low. And the response to hypoxia, it is vasoconstriction instead of vasodilation. It is vasoconstriction because it's a compensatory mechanism for BQ abnormality. Let us now discuss the pulmonary vascular resistance. Okay, if you want to compute for your pulmonary vascular resistance, you can compute it based on Ohm's law, wherein resistance is equal to the driving pressure over that of blood flow. Now, here is a cartoon showing to us the different pressures in the pulmonary circulation and in the venous circulation. Okay, so this is the right ventricle giving rise to the pulmonary artery, pulmonary capillary, pulmonary vein draining into the left atrium. So if we want to compute for the pulmonary vascular resistance, it's input pressure minus output pressure over that of blood flow. Okay, so the input pressure is pulmonary artery, the output pressure is the left atrium, and the flow will be your cardiac output coming out of the right ventricle. Okay, and these are the numbers. Okay, and when we substitute that, that's how we compute for the pulmonary vascular resistance. Okay, the pulmonary vascular resistance, just like your airways, is dependent on the physical dimensions of the tube and likewise of the blood. So resistance is equal to the viscosity of the blood times the length over that of the radius of your pulmonary blood vessels. So as far as viscosity is concerned, it is directly dependent on resistance. The higher the hematocrit, the higher will be the pulmonary vascular resistance. And therefore, this is the basis why in some patients with increased pulmonary vascular resistance, if they have polycythemia, we do phlebotomy. Now, what are the factors that will control the radius of the pulmonary blood vessels? These are the smooth muscle tone, perfusion pressure, lung elastance, alveolar pressure, and lung volume, which interacts with each other. Okay, so listed here are substances which dilates the pulmonary blood vessels and which constricts the pulmonary blood vessels. You're supposed to memorize this for the board exam. And how are you going to memorize it? You just memorize the pure ones. Okay, if it is not in the pure ones, then it is a constrictor. So you just memorize the vasodilator. Okay, if it is not a vasodilator, then you assume it is a vasoconstrictor. Okay, so how do we memorize the vasodilator? The mnemonics is no blood pressure is bad. So nitric oxide, oxygen, bradykinin, prostacyclin or prostaglandin I2, beta-adrenergic stimulation, acetylcholine, and dopamine. Okay, these are the factors that will cause smooth muscle relaxation. Now let us first discuss one of the factors that determines the pulmonary vascular resistance, and that is perfusion pressure. The pulmonary circulation is a very compliant type of a circulation. An increase in blood flow is not accompanied by increase in perfusion pressure nor pulmonary vascular resistance. This is due to the phenomena of recruitment and accommodation. And this will illustrate to you what we mean by recruitment and accommodation. So initially, these blood vessels are open, but there's no blood flow, as you can see here. If there will be increased blood flow, okay, blood will flow to these open blood vessels. Okay, so that is recruitment. These previously blood vessels wherein there's no blood flow is recruited. Okay, the other is accommodation. You notice that the blood vessels are not fully distended. So if there will be an increase in blood flow, okay, aside from the recruitment, there will be dilation of the blood vessels. That is accommodation. Now, there are two types of blood vessels which determine the pulmonary vascular resistance. So, You have your extra-alveolar blood vessels, and you have the blood vessels which is exposed to alveolar pressure, and we call that the alveolar blood vessels. Okay, the extra-alveolar blood vessels are dependent on the lung elastance, while the alveolar vessels, as I mentioned, are dependent on alveolar pressure. Both lung elastance and alveolar pressure are, on the other hand, dependent on lung volume. And how lung volume affects lung elastance and alveolar pressure are opposite each other. That's why the pulmonary vascular resistance relationship to the lung volume is quite complicated. So let us now study the relationship between lung volume, elastance, and extra-alveolar vessels radius. And you will notice that the relationship between lung volume and extra-alveolar blood vessels radius is similar to that of the relationship between lung volume and small airways. Okay, so this is the extra-alveolar blood vessels. As I mentioned to you, it is dependent on the elastance tethering effect on the extra-alveolar blood vessels. We mentioned that the greater the lung volume, the greater is the lung elastance. And therefore, at RB, the elastance is low, so the tethering effect on the extra-alveolar vessel is quite low. So this will be the radius. And at TLC, where there is a high elastance, the tethering effect will be much higher and the radius will be much larger. And therefore, the greater the lung volume, the greater the lung elastance, the greater the extra-alveolar vessel radius, and therefore the lower is the extra-alveolar vessel's resistance. Now let us now examine the relationship between lung volume and the alveolar pressure and the alveolar vessel's radius. Now the alveolar vessel's radius is dependent on the surrounding alveolar pressure. The greater the alveolar pressure, the greater is the compression, the lower is the radius of the alveolar blood vessels. So at RB, okay, there is lesser collapsibility, lesser elastance, and there will be less alveolar pressure, so there will be less compression of the extra alveolar blood vessels. Okay. At TLC, there's greater lung elastance, so there's greater collapsibility, so there's greater alveolar pressure, there's a greater compression of the alveolar blood vessels, and therefore the radius will be smaller. So in essence, what's happening is the greater the lung volume, the greater the alveolar vessels, okay? The lower is the alveolar vessels radius, the higher is the alveolar vessels resistance. So it's exactly opposite that of the extra-alveolar blood vessels. So I mentioned to you that the alveolar vessels is directly related to lung elastance, and the alveolar vessels is inversely related to the alveolar pressure. And both of these are related to the lung volume. And therefore, as we discussed in the previous two slides, this is the relationship. The greater the lung volume, the greater is the alveolar vessels resistance, and the lower is the extra-alveolar vessels resistance. The mnemonics is left atrial enlargement. Lung volume is directly related to alveolar vessels resistance and inversely related to extra-alveolar vessels resistance. So this is the relationship between lung volume and pulmonary vascular resistance. Let's start off with the relationship of lung volume in the x-axis, and the y-axis we're talking about alveolar vascular resistance. Okay, so the greater the lung volume, the greater is the alveolar vessels resistance. And when we go to extra-alveolar vascular resistance, okay, the greater the lung volume, the lower is the extra-alveolar vascular resistance. Okay, your pulmonary vascular resistance is the sum of the resistance offered by your alveolar blood vessels and your extra-alveolar blood vessels. And you can see, if you sum it all up, the pulmonary vascular resistance has this U-shaped configuration. Okay, so this one is the extra-alveolar blood vessels resistance, this one is the alveolar vessels resistance, and this one is the total pulmonary vascular resistance. And as I mentioned, it is U-shaped, and the inflection point is that in the FRC. So the pulmonary vascular resistance total goes down from RB to FRC, then begins to rise again from FRC to TLC. So in the initial part from the RB to the FRC, what is predominant is the extra-alveolar vascular resistance, okay, which influence more the total vascular resistance. And from FRC to TLC, what influence more the pulmonary vascular resistance is the alveolar blood vessels resistance. So let us now go to the effect of gravity on perfusion pressure, alveolar pressure, and blood flow. If the perfusion pressure is greater than the alveolar pressure, this will become distended and there is going to be blood flow. Okay, but if the alveolar pressure is greater than the perfusion pressure, there will be compression and therefore there will be less blood flow. In some situation, if it is totally collapsed, there will be no blood flow. Now, the problem now is the perfusion pressure is affected by gravity, while the alveolar pressure is not affected by gravity. Because of this one, there will be a differential in blood flow from top to bottom of the lungs. Let us now go to the vascular zones of West and let's discuss the principles. There are four zones and we talk about three pressures: alveolar, arterial, venous. You got to memorize this in alphabetical order. Alveolar, then followed by arterial, then the venous pressure. The alveolar pressure is not affected by gravity, while arterial and venous are affected by gravity, as I mentioned. And therefore, I like to think as the alveolar as the skipping pressure. So, in zone 1, the alveolar pressure is greater than the arterial and greater than the venous pressure. In zone 2, the arterial is greater than the alveolar and greater than the venous. So you see this skip to this one. Okay. In zone 3, the arterial is greater than the venous and greater than the alveolar. And in zone 4, it's the same. Arterial is greater than venous, greater than alveolar, but the extra alveolar blood vessels are collapsed. So that's how I memorize the different zones of West. So in zone 1, the alveolar is greater than the arterial and greater than the venous. This does not exist in the normal lung. In zone 2, the arterial is greater than the alveolar, greater than the venous, and the vessels are partially compressed. But there's some blood flow, as you can see here, with gradually increasing blood flow. In zone 3, the arterial is greater than venous and greater than arterial. And notice that the blood vessels are distended. That's why you have the greatest blood flow here. While in zone 4, the relationship is still the same. Arterial is greater than the venous, greater than the alveolar, and the extra alveolar vessels are partially collapsed. Okay, and therefore there is no blood flow at this segment here because it is collapsed. So which of the following constrict the pulmonary arterioles? What is our mnemonic? No blood pressure is bad. So if it is not here, then it is a constrictor. Oxygen is in no. Nitric oxide is in no. Prostaglandin is in BP. Thromboxane is not seen here. So this is the correct answer. This is the vasoconstrictor. Which of the following best describes the pulmonary vascular resistance or the PVR? Our mnemonics is left atrial enlargement and the total pulmonary vascular resistance is U-shaped. The inflection point is at FRC. So the PVR due to extra alveolar vessels is highest at TLC, that is false, because the greater the lung volume, the lower is the extra alveolar blood vessels resistance. Okay? Letter B, PVR due to alveolar vessels is highest at RB, Again, that's false because the greater the lung volume, the greater is the alveolar vessel's resistance. Then, total PVR is higher in RB than in FRC. We looked at with this U shape, and that's right. The PVR is higher in RB than at FRC. That's the correct answer. Total PVR is higher in FRC than TLC. We know that's wrong. The PVR is lowest at FRC. So we move on to the next topic, number 9, which is alveolar ventilation. The respiratory zone starts at which anatomic structure? Part of the airway wherein the cartilage disappears. B. 10th generation of the lower airway. C. 17th generation. And D. 20th generation. Again, I like you to pause, try to answer, then resume. As I mentioned before, the airway is divided by the larynx into your upper airway and the lower airway. And your lower airway is just the trachea undergoing 23 dichotomous branching. The conducting zone is from airway generation 1 to 16, and the respiratory zone is from airway generation 17 to 23. If, for example, an individual is going to inhale a tidal volume of 500 cc, okay, 150 cc of that will be distributed into your upper airway, into your conducting zone, and into your respiratory zone wherein there's a high BQ relationship. And this is known as your dead space volume. Okay? While the 350 will be distributed to the respiratory zone where it undergoes gas exchange because there's an alveoli. And we call that the alveolar space volume. So the tidal volume is then the sum of your dead space volume and alveolar space volume. The tidal volume is usually 5 to 7 mils per ideal body weight in kilograms, while the dead space volume is 2.2 ml per actual body weight in kilograms. The BA is computed. We'll just get the difference between tidal volume and dead space volume, and the BD over BT, which is the physiologic dead space, we just compute it as BD over BT. So for a 60 kilograms times 7, so that's approximately 420 ml of tidal volume. 60 times 2.2, that's around 132 ml of dead space volume. The alveolar space volume is 420 minus 132, that's 288, while the physiologic dead space is 132 over 420. So for 70 kilograms, we multiply that by 7, then that's around 490, but you usually round it up to 500 cc. The dead space volume is 150, alveolar space is 350, and the physiologic dead space ratio is 0.3. What, for example, will happen to these different parameters if there's going to be respiratory center depression? Okay, what's going to happen is the tidal volume will go down, but the anatomic dead space will be maintained, and what will be sacrificed will be your alveolar space volume, and consequently the physiologic dead space ratio will be higher. So let us now discuss alveolar ventilation, which has a lot of physiologic significance. I mentioned that tidal volume is equal to alveolar space volume plus dead space volume. Your minute ventilation, or your BE dot, is equal to tidal volume times respiratory rate. Okay, so we're going to combine these two equations here. So BE dot is equal to tidal volume, which is the sum of alveolar space volume plus dead space volume times respiratory rate. Okay, we're going to multiply RR to this one, and therefore we come out with BE dot is equal to BA plus RR plus BD times RR. Okay, this is known as your BA dot, this is known as your BD dot. Okay, so BE dot is equal to BA dot plus BD dot. Okay, so what we're interested with is your BA dot. Okay, that is what has a lot of physiologic significance. So we're going to place this on this side of the equation, and we're going to transfer this to the other side of the equation. So we come out with BE dot minus BE dot equals BA dot. Okay, if we want to expand BE dot, which is tidal volume times RR, we come out with the final equation, which is tidal volume times RR minus BD dot is equal to BA dot. Now, the BA dot has a lot of significance. Okay, the greater the alveolar ventilation, the greater is the O2 tension, the lower is the CO2 tension. This is seen in this graph here. Okay, the greater the alveolar ventilation, the greater is the O2 tension, and the lower is the CO2 tension. Why is that so? Because alveolar ventilation is the mode of delivery for O2 from the atmosphere into the alveoli, into the body. Alveolar ventilation, on the other hand, is the mode of elimination of carbon dioxide from the body into the alveoli, out into the atmosphere. That's why we have this relationship. So, if the alveolar ventilation will go down, the O2 tension will go down, while the carbon dioxide tension will go up. Okay, so let's apply that with this equation here. So, if the tidal volume will go down, or the RR will go down, or the BD dot will go up, the BA dot will go down. And consequently, the O2 tension will go down, while the carbon dioxide tension will go up. So the respiratory zone starts at which anatomic structure? Part of the airways wherein the cartilage disappear, that is pulsed. Those are known as their bronchioles. Okay. The 10th generation of your lower airway, that's still part of your conducting zone. Okay. Conducting zone is 1 to 16, and your respiratory zone starts from airway generation 17 to 23. So this is the correct answer. Okay. Not the 20th, because the respiratory zone starts at 17. Okay, which of the following is both seen in alveolar ventilation and alveolar gas equation? Okay, A, the PaCO2, B, the PaO2, C, the carbon dioxide production, D, RQ. So I want you to pause, try to answer, then we're going to resume. Let us now talk about the two confusing pulmonary equations, the alveolar ventilation equation and the alveolar gas equation. So there's a ventilation and there's a gas equation. Alveolar ventilation equation is the relationship between the BA dot, which is directly related to the carbon dioxide production of the body, or BCO2 dot, over that of alveolar carbon dioxide tension. While the alveolar gas equation talks about the O2 tension in the alveoli. Okay, it is equal to the inspired oxygen tension minus the quotient of the alveolar carbon dioxide over that of the respiratory equation. Let us talk about alveolar ventilation equation in more detail. Okay, so again, BA dot is directly related to the carbon dioxide production over that of alveolar carbon dioxide. Okay, this has a cause-effect relationship. This may affect this one, or this may affect this one. So we rewrite it this way. So let's analyze the relationship. Okay, if the carbon dioxide production of the body is constant, okay, and the BA dot is going to increase, what is going to happen to the alveolar carbon dioxide tension? It is going to go down. Okay. On the other hand, if the carbon dioxide production of the body is going to increase, and the individual would like to maintain the alveolar carbon dioxide tension constant, the alveolar ventilation needs to increase so that the alveolar carbon dioxide tension will remain constant. Now let us go to the alveolar gas equation. Again, the alveolar O2 tension is equal to the inspired oxygen tension minus the quotient of alveolar carbon dioxide over that of respiratory quotient. Okay, these are the cost variable and this will be the effect variable. So, for example, there will be an increase in alveolar carbon dioxide tension. The alveolar O2 tension will go down. And that's based on Dalton's law. Okay. So, which of the following is both seen in alveolar ventilation and alveolar gas equation? Okay, what are the two confusing equations? Okay, one is the alveolar ventilation equation. So, BA dot is equal to BCO2 over PaCO2. And the other one is alveolar gas equation. So, what's the main variable? It is O2 tension in the alveoli, which is equal to the PiO2 minus the quotient of alveolar carbon dioxide over respiratory quotient. So RQ, is it both seen? No. BCO2, it's not, it's only seen in the alveolar ventilation equation. That's false. The PaO2 is only seen in the alveolar gas equation. And the PaCO2 is both seen in the alveolar ventilation and the alveolar gas equation. So that's the correct one. So let us move on now to the diffusion along the alveolo-capillary membrane. Which of the following is accurate with regards gas exchange along the alveolo-capillary membrane? Under normal conditions, blood stays in the pulmonary capillary 4 times longer than necessary for carbon dioxide to be adequately removed from the blood. B. Compared to O2, CO2 is more diffusible because of a higher molecular weight. C. During exercise, the pulmonary capillary blood transit time is prolonged to promote optimal gas exchange. D. During tachycardia, the pulmonary capillary transit time is shortened and therefore promote hypoxemia. Okay, I'd like you to pause, try to answer, then resume. The diffusion along the AC membrane is governed by the Fick's law of diffusion, which states that the amount of gas that can diffuse along the AC membrane is directly related to the surface area, the solubility of the gas, the pressure gradient across the AC membrane, and inversely related to the thickness of the membrane and the gas molecular weight. So this is the relationship of this equation. These are the cost variable and this is the effect variable. Okay, so the lower the area, the solubility, the pressure gradient, the thicker the AC membrane is, the higher the molecular weight of the gas, the lower will be the amount of gas that is going to diffuse along the AC membrane. Okay, which will have an easier time diffusing along the AC membrane, the carbon dioxide or the oxygen? Initially, you're going to think that the carbon dioxide is going to have a more difficult time diffusing across the AC membrane because it has a higher molecular weight. However, the carbon dioxide is much more soluble than that of oxygen and therefore it diffuses along the AC membrane 20 times easier compared to that of oxygen. Let us now discuss the diffusion of oxygen and carbon dioxide along the AC membrane. The alveolar oxygen tension is 104, while the mixed venous O2 tension is 40, so the direction of diffusion is towards the blood vessel. Okay, so the blood is going to enter at the venous side and going to traverse the pulmonary capillary and ends up here at the arterial end, which is known as the end capillary blood. Okay, notice that the initial net diffusion is from the alveolus to that of the blood in the pulmonary capillary, shown by a bigger arrow going this direction against that of an arrow towards going that direction. Now, at this point here, you can see that both arrows are equal in size, meaning to say that equilibrium is achieved at this level here. And as blood goes from this point till the end capillary, there's no net diffusion because equilibrium is already achieved. Now, with regards carbon dioxide is concerned, the mixed venous CO2 tension is 45, while the alveolar CO2 tension is 40, and therefore the net diffusion will be towards the alveolus. Okay, notice again that here equilibrium is immediately achieved, almost immediately achieved, okay, as blood enters into the pulmonary capillaries. And the rest, as it goes through the end capillary, there's no net diffusion because equilibrium is already achieved. Okay, this is another way of looking at the previous figure. The x-axis is the RBC capillary transit time. The y-axis, there are two. This is for the O2 tension, and this is for the carbon dioxide tension in the mixed venous blood, or the blood in the pulmonary capillary. So initially, the O2 tension is 40. Okay, it goes up as gas is diffused, oxygen is diffusing from the alveolus into the capillary, goes up, and equilibrium is achieved at this point at around 0.23 seconds. And the rest of the time, as the blood is traversing the pulmonary capillary, there's no change in O2 tension because equilibrium is already achieved. While for carbon dioxide, we initially started at 45. Okay, as carbon dioxide diffuses from the blood into the alveoli, it decreases in tension and it achieves equilibrium at this point at around 0.7 seconds. Oh, sorry, around 0.17 seconds. And the rest of the time, there's not much change in the carbon dioxide because it is already in a state of equilibrium. Okay, so this is the normal capillary transit time at rest. It's around 0.75 seconds. And notice that the critical contact time is 0.23 seconds. For RBC to be fully oxygenated, it needs only to stay around 0.23 seconds out of the 0.75 to be fully oxygenated. And the rest of the time, we have a large reserve. Okay? So during exercise, the reserve time, the pulmonary capillary transit time, is going to decrease. Okay, but it seldomly decreases below the critical contact time. So from 0.75, because of the tachycardia, it may go down to 0.5, 0.27, but it seldomly goes down to 0.23 to cause hypoxemia. So we go back to this question here. Which of the following is accurate with regards to gas exchange along the AC membrane? Under normal conditions, let's start from below. During tachycardia, the pulmonary capillary transit time is shortened and therefore promote hypoxemia. That is false. We mentioned it goes down, the pulmonary transit time, but it seldomly goes down below 0.23 seconds, which is the critical contact time. Okay, during exercise, the pulmonary capillary blood transit time is prolonged to promote optimal gas exchange. Again, during exercise, there's tachycardia, the blood transit time is shortened. Compared to O2, CO2 is more diffusible because of a higher molecular weight based on the Fick's equation. Okay, Fick's law of diffusion, that is not true. It is because the carbon dioxide is much more soluble than that of oxygen along the AC membrane. And A, blood stays in the pulmonary capillary 4 times longer than necessary for CO2 to be adequately removed from the blood. And that's the correct answer. Okay, it only needs 0.17 seconds for equilibrium, and it stays in the blood. The blood stays for 0.75 seconds. So this is the correct answer. So let us now move on to the 11th subtopic, which is BQ relationship. Which of the following best describe the respiratory units affected by pulmonary embolism? A, the BQ relationship is 0. B, the alveolar O2 tension is less than 104. C, the alveolar CO2 tension is less than 40. And D, the respiratory units contribute to the alveolar shunt effect. I want you to pause, try to answer, then resume the video. Which of the following occurs in the lower lung zones respiratory units of an upright lung? A. High BQ relationship. B. Alveolar shunt effect. C. O2 tension greater than 104. And D. Shunt effect. Again, I'd like you to pause, try to answer, then resume the video once you have an answer. As I mentioned before, what will determine the respiratory unit's ventilation is compliance and resistance. The greater the compliance, the greater the ventilation, the greater the resistance, the lower is the ventilation. Let us now discuss the ideal BQ relationship. And to simplify things, we're going to think of as the lungs being composed of just two respiratory units, the right and the left, and the pulmonary artery branching into the right and to the left. If the minute ventilation is 6 liters, 3 liters will go to the right and 3 liters will go to the left. If the cardiac output is 6 liters, 3 liters will go to the right and 3 liters will go to the left branch of the pulmonary artery. Okay, if we try to compute for the ventilation over perfusion, BQ, 3 over 3 is equal to 1. And BQ of 1 is known as your ideal BQ. That is the BQ relationship wherein there's optimal gas exchange. From a BQ relationship of 1, okay, there may be alteration. For example, there will may be increased airway resistance or diminished compliance of this respiratory unit here, and therefore instead of receiving 3, it receives only 2 liters of ventilation. 2 over 3 is less than 1, and therefore this type of BQ relationship is known as your low PQ relationship. If, for example, there's total blockade of the ventilation of the airways, the ventilation now will become 0. 0 over 3 is 0, and this is known as a BQ of 0 or a shunt BQ relationship. On the other side, the perfusion may be affected, such as there may be partial blockade of the pulmonary artery. Instead of receiving 3, it just receives 2. 3 over 2 is more than 1, and therefore it's known as your high BQ relationship. Or there may be total blockade of the pulmonary artery, so the perfusion is now 0. 3 over 0 is known as infinity BQ. Now, what are the causes of the BQ abnormalities? Low BQ. Okay, this could either be a high airway resistance, which is going to diminish the ventilation, or low compliance, which is going to diminish the ventilation, such as what you see in pulmonary fibrosis and scoliosis. How about a shunt BQ? Okay, this may be due to a total obstruction due to a foreign body or an extrinsic airway mass producing zero ventilation, or there may be atelectasis collapse. It may be extrinsic compression of the alveoli, such as in hydrothorax or pneumothorax, or a mass which compresses on the alveoli. It may also be passive atelectasis, such as in the case of hyaline membrane disease, wherein there's absence of surfactant. Okay, the alveoli is going to collapse. Or this may be flooded by fluids, as you see in congestion, or exudates, as you see in pneumonia. These diseases will give rise to a shunt BQ. A high BQ relationship can be secondary to the partial obstruction of the blood vessels, as you see in pulmonary embolism, or during a hypotensive state wherein the perfusion will be less than the ideal. A BQ of infinity is seen if there's complete obstruction of the blood vessels, as you see in pulmonary embolism, wherein the perfusion is going to be 0, so 3 over 0 is infinity. Okay, so in COPD or asthma, what is the primary BQ relationship? So there will be obstruction in the airways, there will be diminution of ventilation, and therefore it is a low BQ relationship. How about in pneumonia? What is the BQ relationship? So the alveoli will be flooded by exudates, and therefore the ventilation will be zero, and you have a shunt BQ relationship. How about in hydrothorax? What is the primary BQ relationship? Okay, this pleural fluid is going to compress on the alveoli. It's going to cause collapse of the alveoli, and therefore the ventilation will be zero, and you have a shunt BQ relationship. How about pulmonary embolism? Okay, the blood clot will go to the pulmonary blood vessels, diminishing the perfusion, or in some extreme cases, causing it to be zero, and therefore it gives rise either to a high BQ relationship or a BQ of infinity. How about if there's a hypotensive state? What will be the primary BQ relationship? Again, the Q will be affected. It will go down. So what you're going to have is a high BQ relationship. So let us discuss the relative ventilation of the different types of the BQ relationship. In a high BQ relationship and infinity, you can see that the ventilation is higher than the perfusion. So you say that there's a relative hyperventilation in this respiratory unit. Now, in the low BQ and the shunt BQ, you can see that the ventilation is much lower than the perfusion. So you may say that there's a relative hypoventilation in these respiratory units with this BQ relationship. Now, we go back again to alveolar ventilation. We mentioned that the greater the alveolar ventilation, the greater is the O2 tension, the lower is the carbon dioxide tension. And therefore, if the alveolar ventilation will go down, okay, the O2 tension will go down while the carbon dioxide tension will go up. Okay. So, the ideal BQ, okay, you have an optimal gas exchange, and therefore the alveolar and blood in the pulmonary capillaries is going to have an O2 tension of 104 and a CO2 tension of 40. Okay, what is going to happen if you're going to have a relative hyperventilation? Okay, so in relative hyperventilation, what will happen to the O2 tension? It's going to be higher, while the carbon dioxide tension is going to be lower. Okay, higher O2 and lower CO2. How about if you have low or shunt BQ? What will happen to the O2 and CO2 tension? Okay, the lower the alveolar ventilation, the lower is the O2 tension, and the higher is the carbon dioxide tension. Okay, so those are the consequences of BQ relationship in the O2 tension and CO2 tension in the alveoli and blood in the pulmonary capillaries. So let's have a brief review of what we discussed. So in a BQ relationship of 1, the ventilation is matched with the perfusion, so the O2 tension will be 104 and the CO2 tension will be 40. In a low BQ, there's relative hypoventilation, so the O2 tension will be lower while the carbon dioxide will be higher. And in a zero BQ, there's much more relative hypoventilation, so the O2 is much lower, okay, and the carbon dioxide is much, much higher. Now, in a high BQ, such as in a hypotensive state, there's relative hyperventilation, so you expect the O2 tension to be greater than 104 and the CO2 tension to be less than 40. However, in a BQ of infinity, okay, there's more relative hyperventilation, and therefore the O2 tension will be markedly elevated while the carbon dioxide tension will be markedly low. Now let us analyze now the BQ relationship of the normal lung. Okay, here is the relationship. In the x-axis is from the base going to the apex, and this is the perfusion. Notice as one goes from the base to the apices, the perfusion decreases. Let's do it another way around. As you go from the apices to the base, there's increase in the perfusion, meaning to say that the lower lung zone is 8 times better perfused than the upper lung zone. Let's now analyze ventilation. Again, from base to apex, and ventilation is in the y-axis. notice as you go from the apex to the base, the ventilation increases. Meaning to say that the base, as you can see here, is 3 times better ventilated than the apices. Now, which is more affected by gravity? You can see that the slope is steeper here, so the perfusion is affected more by gravity. And because of this, it gives rise to regional differences in BQ relationship. So we combine the two. This is ventilation. This is perfusion. Okay, notice that in the lower lung zone, the ventilation in blue is less than the perfusion in red, and therefore the BQ relationship is a low BQ. Notice in the apices, in the upper lung zone, the blue, which is ventilation, is greater than the perfusion, and therefore the BQ relationship is a high BQ here. So, in the middle, you have an ideal BQ. Okay, so the auto tension will be 104/40. In the upper lung zone, you have a high BQ, so the auto tension will be greater than 104, and the CO2 tension will be less than 40 because there's relative hyperventilation in the upper lung zone. While in the lower lung zone, you have low BQ. Since you have a relative hypoventilation, the O2 tension will be lower while the carbon dioxide will be higher. So let us now talk about shunt. Shunt is a situation wherein blood was not allowed to have gas exchange with alveolar gas. And there are two types, the anatomic and the alveolar shunt. So we already discussed the two types of anatomic shunt. Now let us shift our attention to alveolar shunt. Alveolar shunt can occur in a BQ relationship of 0 or a shunt BQ or a low BQ relationship. In a shunt BQ or a BQ relationship of 0, notice that in this situation, 3 liters of blood was not given a chance to have gas exchange with air in the alveoli. And this situation is known as your true alveolar shunt. Now, in a low BQ relationship, notice again that not all blood, 1 liter of blood, in fact, was not given a chance to have gas exchange with gas in the alveoli. And this situation is known as your alveolar shunt effect. Going back to the normal upright lung, we know in the lower lung zone, we have a low BQ relationship. And therefore, in our lower lung zone, we have alveolar shunt effect. The total shunt, otherwise known as your physiologic shunt, is a combination of your anatomic and alveolar shunt. It accounts for 4% of the left cardiac output. Pathological shunt may arise, and this may be due to lung diseases which create a low BQ relationship or a BQ relationship of 0. Likewise, cardiovascular diseases, wherein there's passage of blood from the right to the left heart circulation, will give rise to pathologic shunts. Moving on to dead space ventilation, it is a situation wherein inspired air is not allowed to have gas exchange with pulmonary capillary blood. And there are two types, the anatomic dead space and the alveolar dead space. The anatomic dead space is composed of your upper airway and the lower airway's conducting zone, while your alveolar dead space are respiratory units with a BQ relationship of infinity or a high BQ relationship. Notice that in a BQ of infinity, in this drawing here, 3 liters of air was not given a chance to have gas exchange with blood in the pulmonary capillary. In a high BQ, not all of the air in the alveoli, in fact 1 liter, was not given a chance to have gas exchange with blood in the pulmonary capillary. Alveolar dead space exists in our normal upright lung. We know in the upper lung zone, we have a high BQ relationship, and therefore we have alveolar dead space ventilation in our upper lung zone. So, the total dead space, or your physiologic dead space, is composed of the sum of your anatomic dead space and your alveolar dead space. and it is usually 150 ml per 70 kilogram individual or 2 ml of actual body weight in kilogram. So we have our anatomic dead space, which is composed of your upper airway and conducting zone, and you have your alveolar dead space, which are the high BQ relationship in the upper lung zone. The total physiologic dead space, okay, may increase in pathological conditions, which may give rise to an increase in our alveolar dead space. Conditions such as pulmonary embolism or hypotensive state, which gives rise to a respiratory unit with a high BQ relationship. Let us now discuss the BQ mismatching. We got to understand that the respiratory units are connected to each other. So, from an ideal situation of a BQ relationship of 1, pathological condition may set in, such as if there's a partial airway obstruction on the right respiratory unit, okay, instead of receiving 3, it receives 2 liters of ventilation, and 2 over 3 is a BQ relationship of 1. Now, the 1 liter that's supposed to go here is diverted to the other side, and therefore it receives 4 liters, okay, of ventilation over a 3 perfusion, 3 liters of perfusion. So you have a high BQ relationship. Now, in this situation here, okay, you have a shunt BQ or a BQ of 0. The 3 that's supposed to go here is diverted to the left side, okay, and therefore you have 6 over 3, and likewise, you have a high BQ relationship. So, you have a shunt BQ or a low BQ. It indirectly gives rise to a high BQ relationship, and therefore it increases the alveolar dead space. Moving on to the other side of the illustration, pathological condition may occur in the pulmonary circulation, such as partial obstruction of the blood vessels, such as in pulmonary embolism. Okay, the instead of 3, it only receives 2. So you get the BQ relationship. That's 3 over 2. That's a BQ of greater than 1. The 1 liter that's supposed to go here goes to the other side. So you have a 3 over 4 BQ relationship, which is less than 1. Okay. In this situation here, you have total obstruction of the blood vessels going to the right. So the ventilation is 0. 3 over 0, I mean the perfusion is 0. So 3 over 0 is a BQ of infinity. The 3 that's supposed to go here is diverted to the other side. So it gives rise to a BQ relationship of 3 over 6, which is a BQ less than 1. So a high BQ relationship or a BQ of infinity indirectly gives rise to a low BQ, which is going to give rise to alveolar shunt effect. Now, what is the consequences of this BQ mismatching? Under normal condition, our physiologic dead space ventilation is due to the ventilation of our anatomic dead space and our alveolar dead space, which are located in the upper lung zone. Now, pathological condition may occur, which can give rise to BQ mismatching, producing a high or a BQ of infinity, and therefore it adds to alveolar dead space. And therefore, during BQ mismatching, our physiologic dead space ventilation increases, and consequently, our alveolar space ventilation decreases, which will lead to hypoxemia and hypercapnia. So what are the compensatory mechanisms for a primarily low BQ or a zero BQ? From an ideal situation, okay, ventilation problem may occur, and it may give rise to a low BQ and indirectly give rise to a high BQ relationship. Now, the compensatory mechanism that is going to be instituted by the respiratory system is in the circulation. What's going to happen is there is going to be a hypoxic vasoconstriction. Notice that the BQ relationship here is low, and therefore there will be hypoxemia or hypoxia, and the response of the pulmonary circulation will be to constrict. What will the constriction do? Notice what's going to happen. Instead of 3 going here, it's going to be 2.5, then partially correcting the low BQ here. Okay, likewise, the vasoconstriction here will divert the blood that's supposed to go here towards this side, and therefore you're going to have a Q of 3.5 and therefore partially correcting the high BQ relationship. So the hypoxic vasoconstriction will partially correct the BQ mismatching. What is then the compensatory mechanism for a primarily high BQ or a BQ of infinity? Now, from a normal condition, there may be perfusion problem. There's partial obstruction here. So you have a BQ relationship that's 3 over 2 or infinity. And the blood that's supposed to go here goes here. So you have a BQ relationship of 0. What will be the response? Since the problem is in the perfusion, the response will be in the ventilation. So what's going to happen is there's going to be bronchoconstriction. So instead of 3, the ventilation in this respiratory unit will be around 2.5 because of the bronchoconstriction, partially correcting the high BQ relationship. From a 3.2, it partially corrects it to 2.5 over 2. And the air that's supposed to go here is directed here. So instead of 3, it receives 3.5. So it partially corrects the low BQ of 3 over 4 to a partially corrected 3.5 is to 4. Okay, so it partially corrects the BQ mismatching. So if the primary abnormality is in the ventilation, which will give rise to a low BQ or a shunt BQ, the response will be in the circulation in the form of hypoxic vasoconstriction. Now, if the primary BQ abnormality occurs in the perfusion, such as in a high BQ or BQ infinity, the response will be in the ventilation and there will be bronchoconstriction. So the rule of thumb is the other component, the V or the Q, will compensate. So going back to this interactive question, which of the following best describe the respiratory units affected by pulmonary embolism? So in pulmonary embolism, there may be partial or complete blockade of the pulmonary capillary, and therefore it is going to give rise to a high BQ or a BQ of infinity. And therefore the BQ relationship is 0 is wrong. Okay, again, we discussed it's supposed to be high or a BQ of infinity. The alveolar O2 tension is less than 104. We have relative hyperventilation in a high or a BQ of infinity, and therefore we expect the oxygen tension to be greater than 104. Okay, the alveolar CO2 tension is less than 40. Again, we have a relative hyperventilation, so we expect the carbon dioxide to be lower, and therefore this is the correct answer. The respiratory units contribute to alveolar shunt effect. We only see alveolar shunt effect in a BQ relationship that is low BQ relationship. So that is false. Okay, a high or infinity BQ gives rise to alveolar dead space. So the correct answer is C. The alveolar CO2 tension is less than 40. Interactive question number 17. Which of the following occurs in the lower zones respiratory unit of an upright lung? High BQ relationship. We know in the lower lung zone, it has a low BQ relationship. Okay, that's false. Alveolar shunt effect. Since it is a low BQ relationship, yes, it can give rise to alveolar shunt effect. O2 tension greater than 104. Since we have a low BQ, we have relative hypoventilation, and therefore the O2 tension will be less than 104. Shunt BQ, we don't have a shunt BQ in the lower lung zone. It is only a low BQ relationship. The correct answer is alveolar shunt effect. Let us now discuss the second to the last topic, which is gas transport. Which of the following is the correct Fick's equation? BCO2 is equal to cardiac output times the arterial O2 content. BO2 is equal to cardiac output times the mixed venous O2 content. Oxygen consumption is equal to cardiac output minus the difference between the arterial and mixed venous O2 content, and O2 consumption is equal to cardiac output times the sum of the arterial and mixed venous O2 content. Again, pause, try to answer, and resume once you have an answer. So oxygen from the alveoli is transported into the blood into two forms. One, it's dissolved in physical solution, and the other one, it is bound to hemoglobin. Okay, if we want to compute for the O2 content of arterial blood, that is CaO2, arterial blood content of oxygen, we have to compute for the amount in physical solution and the amount for hemoglobin, bound to hemoglobin. To compute for the amount in physical solution, we multiply 0.003 times the arterial O2 tension. And when we want to compute for the amount of oxygen bound to hemoglobin, we use this formula. Hemoglobin in grams per deciliter times 1.34 times O2 saturation. O2 saturation is determined by your hemoglobin O2 dissociation curve. Let's analyze this hemoglobin O2 dissociation curve. In the hemoglobin O2 dissociation curve, the x-axis is oxygen, the y-axis is saturation. You can see that the higher the arterial oxygen tension, the higher is the hemoglobin O2 saturation. But the relationship is not linear, it is sigmoidal. It has a steep part from 0 to 60, and it has a flat part from 60 and beyond. Now, let me introduce you to the concept of the P50. P50 is the O2 tension wherein the hemoglobin is 50% saturation. Okay, so the hemoglobin is 50% saturation. So that's around here. So at 50% saturation, the arterial O2 tension is around 27. Okay, so normally the P50 is 27 and P50 is the arterial O2 tension wherein the hemoglobin is 50% saturated with oxygen. So let us now compute for the oxygen content of arterial blood. Usually, the arterial blood has an arterial O2 tension of 95. At 95, you can see that the hemoglobin is 97% saturation. So what's the formula? How do we compute for the amount of oxygen dissolved in physical solution? Is 0.003 times the arterial O2 tension. So 0.003 times 95 is equal to 0.28 ml. How do we compute for the amount bound to hemoglobin? Okay, hemoglobin times 1.34 times O2 saturation. Okay, hemoglobin times 1.34 times O2 saturation is 15 times 1.34 times 97, that's 19.5. So we sum it all up. Okay, that's around 200 ml per liter of blood. So normally, the arterial O2 content is around 200 ml of blood. Now let's compute for the O2 delivery to the tissue, or the DO2, delivery of oxygen to the tissue. We mentioned that the arterial O2 content is 200 ml per liter, and the cardiac output is usually 5 to 6 liters. So 5 times 200, okay, the O2 delivery is equal to cardiac output times arterial O2 content, 5 times 200. So normally, we're delivering 1,000 ml of oxygen per minute to our tissues. Okay, so what are the factors that will affect the O2 delivery to the tissues? So DO2 is equal to cardiac output times CaO2. And how do we compute for your CaO2? Okay, it is the amount in physical solution plus bound to hemoglobin. What's the formula for in physical solution? It's 0.003 times oxygen tension. Bound to hemoglobin, 1.34 times hemoglobin times O2 saturation. Okay, so we come out with these factors that will determine O2 delivery. So, for example, there will be a low O2 saturation, there will be low hemoglobin, okay, there will be a low oxygen tension, or the cardiac output will be low, the O2 delivery to the tissues will be low. Now, let us now discuss the O2 content of mixed venous blood. Okay, it is represented as CvO2. Venous blood content of oxygen. Okay, so how much is the oxygen content in venous blood? Well, we use the same formula. CvO2 is equal to in physical solution times hemoglobin. But this time we're using venous blood. And venous blood has an O2 tension of 40 and a saturation of 75. So in physical solution, 0.003 times 40 bound to hemoglobin, the same hemoglobin, 15 times 1.34, but this time the saturation is 75 instead of 97%. So the total amount of oxygen in venous blood is 0.12 plus 15. That's roughly around 150 ml per liter of blood. Okay, so the mixed venous blood has a content of 150 ml, and if the right cardiac output is 5 liters, the amount of oxygen delivered to the pulmonary capillaries is roughly around 750 ml. Okay, so let's now go to oxygen consumption. Okay, if the amount of oxygen delivered to the tissues is 1000 ml per minute, and the amount of oxygen leaving from the tissues in the venous blood going into the pulmonary circulation is 750 ml per minute, how much was extracted by the tissues? So, simplistically, to compute for the VO2, which is the O2 consumption, we just get the difference of the amount delivered, cardiac output times arterial O2 content, minus the amount of O2 leaving the pulmonary circulation and being delivered to the pulmonary circulation. So that's CO2 times C, venous O2 content. So this is the Fick's equation for the computation of O2 consumption. Okay, and we can rewrite it in a short term, cardiac output times the difference between the arterial O2 content and the mixed venous O2 content. So which of the following is the correct Fick's equation? Cardiac output times arterial O2 content. That's false. That's the O2 delivery equation. Cardiac output times CbO2. That's false. That's the O2 delivery to the pulmonary capillaries. Cardiac output times the difference between arterial and mixed venous blood O2 content. That's the correct answer. It is not cardiac output times the sum of arterial and mixed venous O2 content. Okay, question 19. Which of the following is correct with regards to a right shift of the hemoglobin O2 dissociation curve? A. Hemoglobin affinity to O2 increases. B. P50 rises. C. Hemoglobin rejects carbon dioxide. And D. Associated with a low hydrogen ion content. Again, I like you to pause, try to answer, and resume once you have an answer. So let us now discuss the shifting of the hemoglobin O2 dissociation curve. Now, this is the normal position of the hemoglobin O2 dissociation curve. It may shift to the right or shift to the left. Okay, so at a normal position, at a O2 tension of 50, the hemoglobin is 85% saturated. Okay, an increase in your hydrogen, carbon dioxide temperature or 2,3 dPg is going to shift the curve to the right. So what will happen if there will be shifting to the right? Okay, again, at an oxygen tension of 50, let us see what will be the saturation if the curve is shifted to the right. We can see that the saturation is 79. So from 85, when it is shifted to the right, it is less saturated. So meaning to say that the hemoglobin is rejecting oxygen. Okay? So a rise in your 2,3-DPG, hydrogen, carbon dioxide, and temperature will cause the hemoglobin to reject oxygen. This will cause a reduction of your O2 saturation, and this will lead to the right shift of the curve. So it is the rule of R. Now, let us see what is going to happen to the P50 if the curve is going to shift to the right. P50 is the O2 tension where the hemoglobin is 50% saturated. So we know at 50% saturation, a normal position is around 27. What will happen if it is shifted to the right? Okay, when it is shifted to the right, we can see that the P50 increases from 27 up to 32. So meaning to say, a rise in your 2,3-H cut is going to cause hemoglobin to reject oxygen. It is going to lead to a right shift of the curve, and this is manifested as a rise in your P50. Lowering of your 2,3-H cut, on the other hand, will make hemoglobin loves oxygen, okay, and therefore leads to the left shift of the curve manifested as lowering of your P50. Okay, so that's how you're going to remember the shifting to the left and to the right of the hemoglobin O2 dissociation curve. It is the rule of R's and the rule of L. So let us now analyze what is going to happen to the hemoglobin O2 dissociation curve during carbon monoxide poisoning. As illustrated here, during carbon monoxide poisoning, okay, the carbon monoxide displaces, okay, the oxygen and carbon dioxide from the hemoglobin, and therefore the transport of oxygen and carbon dioxide is severely hampered. Now, aside from that, the carbon monoxide is going to displace the hemoglobin O2 dissociation to the left, and therefore, in this situation, the hemoglobin loves oxygen and hemoglobin doesn't want to release oxygen. So it's a double whammy. Aside from the carbon monoxide displacing oxygen from the hemoglobin, the remaining hemoglobin with bound O2 does not want to release the O2 to the tissues, and therefore there will be severe tissue hypoxia. Moving on to the unloading of oxygen in the systemic capillaries. Okay, the arterial O2 tension is 95, while in the tissue it is 23. And therefore, the pressure gradient favors the movement or the diffusion of oxygen from the arterial blood into the tissues. And the amount of oxygen remaining in the venous blood will produce an O2 tension of around 40. Let us now discuss the Bohr's effect. It occurs in the systemic capillaries. So this is the RBC with the oxygen bound to the hemoglobin, and these are the tissues, okay, the cells of the tissue. Okay, the cells produce a lot of carbon dioxide and hydrogen, and they're going to cause the hemoglobin O2 dissociation curve to shift to the right. Remember, 2,3-H cut will cause the curve to shift to the right. This will make hemoglobin reject oxygen, and the rejection of oxygen will favor the unloading of oxygen into the tissues. Let us now discuss internal respiration. Under normal condition, we inspire around 200 ml per minute of oxygen. And that 250 ml of oxygen is used by our tissues in aerobic metabolism. Aerobic metabolism likewise produces 200 ml of carbon dioxide that is subsequently expired by our respiratory system out into the atmosphere. Okay? The ratio of the carbon dioxide production over that of the O2 consumption is known as your respiratory quotient. Okay? The ratio of the carbon dioxide production over that of the O2 consumption is known as your respiratory exchange ratio. Okay, what's the difference? If you get the ratio at the tissue level, that is known as your respiratory quotient. If you get the tissue in the expired gas, that is known as your respiratory exchange ratio. So the respiratory quotient, okay, is equal to the carbon dioxide production of the body over that of the consumption. And it's usually zero point 0.8. Okay? This is sometimes hard to remember. The RQ is equal to BCO2 over BO2. So it's alphabetical, CO2 over O2. Now, normally it's around 0.8 and it may be altered depending on what is the predominant food that we're consuming. If it is predominantly carbohydrates, the RQ becomes 1. Proteins, it's zero point 0.8. Fats becomes lower than zero point 0.8, which is 0.7. So let us now discuss the concept of hypoxemia and hypoxia. Hypoxemia is low oxygen tension. Again, it's low oxygen tension in the arterial blood. Hypoxia, on the other hand, is the inability of the tissue to use oxygen due to either or an low O2 delivery or mitochondrial enzyme problems. What are the causes of hypoxemia? A low arterial O2 tension, a low inspired oxygen such as in high altitude, hypoventilation wherein there's CNS depression the minute ventilation goes down, AC membrane diffusion problems such as interstitial lung disease, BQ mismatching such as in primary lung disease, circulatory shunts such as your cyanotic heart disease. So these are the 5 causes of hypoxemia. Hypoxia, on the other hand, is caused by low O2 delivery or mitochondrial enzyme problem. And when we review the O2 delivery equation, we can see that the cause of low O2 delivery could either be a low saturation, low hemoglobin, low arterial O2 tension or hypoxemia, a low cardiac output. And therefore, the low O2 delivery as a cause of hypoxia can be further subdivided to that of hypoxemic hypoxia and the non-hypoxemic hypoxia. In the hypoxemic hypoxia, this is the cause, the low arterial O2 tension is the cause of the low O2 delivery. And the hypoxemia could either be due to what we discussed earlier, a low PaO2, CNS problem, AC membrane problem, BQ mismatch, and shunt anomaly. So for the non-hypoxemic hypoxia, it may be due to a low cardiac output or low hemoglobin. So therefore, a low cardiac output or hemoglobin problem such as a low hemoglobin level or defective hemoglobin such as in methemoglobinemia. Mitochondrial enzyme problem is another cause of tissue hypoxia. There may be adequate O2 delivery, but the mitochondria cannot use the delivered oxygen, such as if there's cellular enzyme dysfunction or cyanide poisoning. Now, what are the modes of transport of the carbon dioxide produced by the tissues? One is in physical solution, either inside the RBC or in the plasma. Two, it can bind to hemoglobin. Three, it can be transported as bicarb, which is the predominant form. So carbon dioxide binds with hydrogen, produces your carbonic acid, dissociates into your bicarb and hydrogen. Bicarb moves out of the cell. In exchange, chloride moves in. That is known as your chloride ship. It is an osmotically active substance. It attracts water, and this is the reason why the venous hematocrit is much larger than the arterial hematocrit. Now, let us now discuss Haldane's effect. Haldane's effect occurs in the pulmonary capillaries. And as you know, in the pulmonary capillaries, the alveoli, there's a low CO2 tension. Okay? The low CO2 tension is going to shift the hemoglobin O2 dissociation curve to the left, which means that hemoglobin loves oxygen. And therefore, oxygen will go and bind to the hemoglobin, and displaces carbon dioxide, so it is going to be eliminated out into the alveolus into the atmosphere. Okay, so Bohr's effect occurs at the systemic capillaries. The stimulus is the high carbon dioxide and the high hydrogen produced by the tissues. It causes the hemoglobin O2 dissociation curve to shift to the right. It makes hemoglobin unloads oxygen. Okay. Haldane's effect occurs in the pulmonary capillaries. The stimulus is a low carbon dioxide, okay, which causes the hemoglobin dissociation curve to shift to the left. Okay, and therefore hemoglobin loves oxygen. Okay, oxygen will bind to hemoglobin, displacing carbon dioxide, and therefore this favors carbon dioxide unloading in the pulmonary capillaries. So let us analyze the differences between the hemoglobin O2 and the CO2 dissociation curve. This is the hemoglobin O2 dissociation curve. It is sigmoidal, and therefore the hypoxemia of a low BQ cannot be fully compensated by hyperoxemia of a high BQ. Now, this is the CO2 dissociation curve. You can see it is almost linear, and because of this, the hypercapnia of a low BQ can be fully compensated by the hypocapnia of a high BQ. Okay, let me illustrate that further. So you have a BQ mismatching here. Okay, because of those obstruction, it gives rise to a low BQ, which gives rise indirectly to a high BQ. Okay, let's talk about the oxygen tension. Because of the low BQ, it is hypoxemia on the right side and hypercapnia on the left side. And when we try to average this, okay, the hypercapnia cannot compensate for the hypoxemia, and therefore the O2 tension will be below the expected average of 100. Instead, it is 75 because this one cannot fully compensate for this one because the shape of the hemoglobin O2 dissociation curve is linear. When we look at the carbon dioxide tension, this one is going to have a hypercapnia and this one is going to have a hypocapnia secondary to the high BQ relationship. And when we average it, we come out with the real average of 30 plus 50 divided by 2 is 40. Meaning to say this one was able to fully compensate for this one because the shape of the CO2 dissociation curve is linear. So let's discuss this 19th interactive question. It reads, which of the following is correct with regards to the right shift of the hemoglobin O2 dissociation curve? The hemoglobin affinity to the O2 increases. Actually, if there's a right shift, the hemoglobin is rejecting oxygen, that's false. Okay, so a right shift is associated with a rise in your P50. That's the correct answer. Okay, hemoglobin rejects CO2. Hemoglobin rejects O2, not CO2. Okay, associated with a low hydrogen ion concentration, it is a rise in your 2,3-H cut, which causes a right shift of your curve. So therefore, it is not a low hydrogen, but a high hydrogen that causes a right shift of the curve. Okay, so the correct answer is P50 rises. Okay, we now go to the last topic, which is the control of breathing. Okay, which of the following is the central chemoreceptor most sensitive with? Arterial O2 tension, arterial carbon dioxide tension, CSF CO2 tension, or CSF pH. So the purpose of the control of respiration is to establish an automatic rhythm for the contraction of the respiratory muscle. This rhythm should match the following: the metabolic demands, the non-ventilatory events, and varying mechanical conditions. Now, let us discuss the respiratory-related neurons, and there are three types. The interneurons, which makes interconnection to the other respiratory-related neuron, the premotor neuron, which innervates the motor neuron, and the motor neuron, which innervates the ventilatory muscles. So this is another way of looking at the respiratory-related interneurons. Okay, you have the motor neurons, which innervates the respiratory muscle. Then you have your premotor neurons, which innervates the motor neuron. Then finally, you have your interneurons, okay, which makes interconnections with the other respiratory-related neurons. Okay. The first is the ventral respiratory group. It is this one. Okay. It contains inspiratory and expiratory neurons and therefore stimulates your inspiratory and expiratory muscles. It generates the tidal breathing. Okay. And it is modified by inputs coming from the pontine respiratory center and the dorsal respiratory group. The DRG, which is this one, receives sensory information from the chemoreceptors and mechanoreceptors. It stimulates the BRG so that the breathing pattern will change depending on the O2 and CO2 needs of the individual, acid-base balance, and other metabolic demands. So, it is a metabolic feedback for the VRG. Okay, the pontine respiratory center, which is this big one here, receives sensory information from the higher centers and the peripheral chemoreceptors. It inhibits the BRG so that the breathing pattern will change during speaking, sleeping, and exercising. Okay, so the central pattern generator is actually mainly composed of the VRG. Okay, it fires the inspiratory neuron, fires in a ramp-like manner, stops firing, then you have your expiration. So this is the one that is responsible for tidal breathing. Okay, it receives inhibitory signals coming from the pneumotoxic or the pontine center and the dorsal respiratory group, such as, for example, there's metabolic acidosis, there's less inhibition from the DRG or the pneumotoxic group, and therefore the tidal volume will be deeper, higher in tidal volume during metabolic acidosis. Now, what are the inputs to the respiratory related neurons? As shown here, the first one is coming from the higher centers. This is responsible for the ventilatory accommodation for activities such as speaking, playing the musical instrument, swallowing, and vomiting. Then you have the respiratory mechanoreceptors, which detects changes in respiratory mechanical properties such as in congestive heart failure or in asthma. Then you have those irritant receptors in the airways, which is responsible for the change in the ventilatory pattern in the presence of noxious stimuli. You have your chemoreceptors, which is responsible for the ventilatory adjustments due to the metabolic demands of the body. And finally, you have the muscles and joint receptors, which is responsible for the ventilatory adjustment during different activities. Let us now discuss the consequences of receptor stimulation. Stimulation of your stretch receptor located in your airway smooth muscle during inflation will shorten the inspiratory time and increase duration of expiration. Okay, this is known as your Herring-Brewer inflation reflex. It is stimulated by inflation, and the response is to prevent hyperinflation. Stimulation of your stretch receptor, also located in your airway smooth muscle during depletion, is going to trigger a diminution in the duration of your expiration. This is known as your Herring-Brewer depletion reflex. And this Herring-Brewer depletion reflex is stimulated by depletion, and the response is to prevent over-depletion. Irritant receptors may be stimulated in the airways, epithelial cells. The stimulus are your noxious gases, allergens, lung inflammation, and the response will be a rapid shallow breathing, coughing, bronchoconstriction, or hypersecretion. Okay. The juxtacapillary or the J apparens located in the interstitium near the pulmonary capillaries can become engorged during pulmonary edema, and the pattern response in breathing will be a rapid and shallow respiration. They're chest wall receptors. These are the intrapusal fibers in the intercostal muscles, which can be stimulated by stretch. And this is responsible for the maintenance of our tidal volume. Now, let's discuss the chemoreceptors. The peripheral chemoreceptors are very sensitive, most sensitive to a low O2 tension. They're slightly sensitive to a high carbon dioxide tension and a low pH. The central chemoreceptor, on the other hand, has a peculiar sensitivity. Okay, so carbon dioxide from the blood will enter and will form carbonic acid and hydrogen. It is the diminution in the CSF pH which directly stimulates your central chemoreceptors. So it is most sensitive to the change in hydrogen ion in the CSF brought in directly by changes in the carbon dioxide. So let us look at the respiratory control in action. We are familiar with this equation here. Then let's see how will the respiratory center adjust when there are changes in these variables. Okay, for example, there will be pathological conditions which may cause BQ mismatching. And as we mentioned, if there's BQ mismatching, there's increased physiologic dead space ventilation. It is going to markedly decrease the alveolar ventilation and consequently lead to hypoxemia and hypercapnia. The hypoxemia and hypercapnia is going to stimulate the peripheral and central chemoreceptors, and the adjustment will be carried out by the ventral respiratory group. And the command will be to increase the tidal volume and the respiratory rate. This is going to partially correct the low alveolar ventilation and partially correct the hypoxemia and the hypercapnia consequently. So that is the setup, the purpose of your, one of the purpose of your respiratory center. So, which of the following is the central chemoreceptor most sensitive with PO2? No, that's the peripheral. PaCO2, well, not really. It stimulates the central indirectly. The CSF CO2 tension? No. Okay, it is actually the CSF pH. So we go now to the final segment summary. The pulmonary vasodilators, the mnemonics is no BP is bad. There are 4 zones of West with 3 pressures. In alphabetical order, it's alveolar, arterial, and venous. The alveolar is the skipping pressure, which gives rise to the 4 zones of West. Zone 1 does not exist in a normal upright lung. The greater the lung volume, the greater the alveolar pressure, the lower is the AB radius, the higher is the alveolar vessel resistance. The greater the lung volume, the greater the elastance, the greater is the extra alveolar blood vessels radius, the lower is the extra alveolar blood vessels radius. So, the greater the lung volume, the higher is the alveolar vessel resistance, the greater the greater the lung volume, the lower is the extra-alveolar vascular resistance. The total resistance is a combination of your alveolar and extra-alveolar, and it assumes a U shape. The lowest pulmonary vascular resistance is seen at FRC. The lower airway is just the trachea undergoing 23 dichotomous branching. It is divided into your conducting zone and respiratory zone. Conducting zone is airway generation 1 to 16, while respiratory zone is airway generation 17 to 23. In the large airway, it is a turbulent flow, while in the small airway, it is a laminar flow, while in the respiratory zone, the flow of air is by diffusion. The alveolar ventilation equation, as shown here, shows to you the relationship between the BA dot and the alveolar carbon dioxide tension, while the alveolar gas equation shows to you the relationship between the alveolar O2 tension and the carbon dioxide tension in the alveoli. Diffusion equilibrium is achieved at 1/3 of the pulmonary capillary blood transit time. we have a lot of reserve for tachycardia. Okay, the BA dot equations is primarily a combination of your BE dot is equal to tidal volume times RR. Tidal volume is equal to your alveolar space volume plus your dead space volume. And when we combine both, we come out with the equation that BA dot is equal to tidal volume times RR minus BD dot. If there's a relative hyperventilation of the respiratory unit, that will lead to a high O2 tension and a low CO2 tension. RUs with a low or a shunt PQ, there's relative hypoventilation and they're secondary to airway, lung parenchymal, and thoracic cage problem. While respiratory units with a high or BQ of infinity, they have relative hyperventilation and they're usually secondary to pulmonary problems. So these are the different types of BQ. A BQ of 1 produces a normal oxygen and a normal carbon dioxide. In a low BQ and 0 BQ, there's relative progressive hypoventilation and therefore there's a relative progressive hypoxemia and a relative progressive hypercapnia. In a high BQ and a BQ of infinity, there's a relative increase in hyperventilation and therefore there's a relative increase in the hyperoxemia and a relative decrease in the hypocapnia. The upper lung zone is a high BQ relationship. It is where you find the alveolar dead space. While in the lower lung zone, you have a low BQ relationship. It is where you find the alveolar shunt effect. The O2 content is equal to the amount of oxygen in physical solution and the amount of oxygen bound to hemoglobin. The BO2 dot based on the Pick's equation is equal to the cardiac output times the difference between the arterial O2 content and the mixed venous blood O2 content. The hemoglobin O2 dissociation curve is sigmoidal and it follows the rule of R. A rise in your 2,3-H cut makes hemoglobin rejects oxygen. This will cause a right shape of the curve and this will cause a rise in your P50. The Herring-Brewer inflation and depletion reflexes are triggered by inflation and depletion respectively. The central chemoreceptors are directly responsive to the CSF hydrogen and indirectly responsive to the arterial carbon dioxide tension, while the peripheral chemoreceptors are primarily responsive to arterial O2 tension. So with that, thank you very much for your attention. I hope this review is helpful and at the same time enjoyable. God bless and make us proud during the board exam.